Good morning, Denise. How are you?
Hello, Mr. King. Good morning.
Mhm. Hope everything's going okay.
Yes, everything's great.
Good. Good job on your exam.
Thank you.
Mhm. Okay, so we begin, well, we already started chapter 9, and then today it starts to get to be more interesting, I hope. And what we learn today will carry us through section 9.2, of course, 9.3, 9.4, 9.5, and 9.6. So what we cover right in the next 20 minutes or so is going to serve us well for those sections to come, because this
Okay.
section and the sections to come are asking us to explore the same idea with different techniques. Yeah, just
Mm-hmm.
like we learn how to integrate with different techniques, we're going to learn how to do what I'm about to talk about with different techniques. So
Okay.
so if we understand the idea of the next 20 minutes or so, then that makes this chapter fairly simple to do. That's the goal, okay?
Okay.
Okay, so, all right. So, do you see the web assign here on your
Yes.
screen? Okay.
Mm-hmm.
And I want, well, what do I want to do? I think it's best to, I don't want to start, most of the time I kind of start with the problem, but I want to do a little background
Mm-hmm.
discussion. And
Okay.
for that, we'll go to my notebook, which I don't have any notes yet, um, but that's what I'm going to do. We're going to do to get that first 20 minutes of the topic I was talking about.
Okay.
So, and Jocelyn is coming, so that's good. Okay, so all right, I'm gonna, as I mentioned, and go to my notebook, even though it's a blank page. And here we go. Good morning, Jocelyn.
Good morning.
How are you doing?
Good in yourself?
What did you say? I heard in yourself. What did you say though?
I said good and yourself?
Oh, good in yourself. Oh, I'm doing well. Thank you.
Yes.
Okay, well, good job on your exam. And here we go. So, as I mentioned to Denise, the first 20 minutes are really the most crucial part in terms of understanding, uh, hopefully in a good perspective, a solid, strong perspective of what the next 5 sections are about, because they're all about the same idea. It's just, and that's what I'm about to talk about, and it's just those following 5 sections are different methods to do the same thing. So, um, so I want to just start by kind of just talking about some things. And the first thing I want to do is really just a reminder. And so here we go. So reminder. So let's consider a sequence. And I'm gonna pick, and we'll say a sequence A sub n, could call it V sub n, doesn't matter. So therefore, we'll start with n equals 1 as the first term. So instead of starting at A sub 2 or A sub 3 or a sub 0. So 1, and I'll just pick some number here. So how about 3? Okay. And then I want us to write a few terms down. And the terms to follow, well, if we had a formula, we could clearly use the formula and just plug in the n value to find each term. So at this one, you would put a 2 into the formula and you would get the next term and so on. But I'm purposely not writing, and this goes on forever, and I'm purposely not writing a formula to remind us of a certain type of sequence. So instead of writing a formula, I'm just going to describe the idea in words. So this sequence is where each subsequent term is, say, multiplied by 3. Or we could say tripled. Okay, so then, and oh well, I'm gonna change my mind here just because I used 3. How about we call the first term 2? Okay, so then simply then to get to the next term, we would multiply by whatever I just made up, which of course, what did I say? We're gonna multiply by
3.
by 3. So 2 times 3 then will be
6.
6 times 3 will be
18.
18 and so forth. Yeah, 54 if I'm multiplying correctly. 3 times 54, 162, and so on. Okay, so when we get this type of sequence, when each subsequent term is found by multiplying by the same number all the time, then this is a specific type of sequence that we studied. There's only 2 types of patterned sequence that we studied in pre-calculus 2, and this was one of them. And this is called a geometric sequence with the common ratio, or we could say the common, Josh is here, with, and you could think you would say the common multiple, but they call it the common ratio, which I can describe. With the common ratio R for ratio, in this case, the number we're multiplying by all the time is a 3. And good morning to you, Joshua.
Good morning.
Okay, so the reason it's called a common ratio, just as a reminder, why is it called a ratio? Because if we compare any 2 consecutive terms, so if we pick, say you pick these 2, and you take the rightmost term and divide it, so this would be a ratio, R, and 54 divided by 18 is 3. And if you picked another 2 consecutive terms, say you picked 6 and 18, well, and you divide and you look at their ratio, well, you get 3 again. And so these ratios are common, meaning they're equal. And this would happen for any 2. You have to pick 2 adjacent terms. And then you pick the right number, the right term divided by the previous term. And that's why they call it a common ratio. And common ratio R. And so that's one thing as a reminder. Also in pre-calculus 2, because this is such a nice type of sequence, it doesn't require any calculus topic to be able to do the following. So here's a sequence. And the common ratio R equals 3. And one thing we did in pre-calculus was we looked at what happens if you start to add these up forever. Okay, but trying to keep my mind straight here in terms of how I want to present all this to you. Okay, so so first of all, so that's the introduction to, well, we already introduced sequences, but this is an example of a geometric sequence. Okay, I'm gonna pick another one. And so here's a second sequence. And let's say we start with first term, a sub 1, and that's when n equals 1, of course, being redundant here. But so we have a sequence a sub n again. I could have used b sub n or something. But anyway, let's say this right here is whatever. So a 1. And the next term can be computed with a formula, but instead of the formula, I'm gonna make it geometric again. So let's say this has a common ratio R equal to 1/3. Okay, so then because it's geometric, and we're being told it's geometric, then to get the subsequent terms, we simply multiply by whatever number they ask us to, which we just made up as 1/3. So of course, and the first term doesn't have to be a 1, it could be anything except 0. That would not be very interesting, because 0 times anything would just be zeros forever. So of course, 1 times the common ratio 1/3 is 1/3. 1/3 times 1/3 is 1/9. Times 1/3 is 1/27. Times 1/3 is 1/81, etc. Okay. So, and if we were asked to, if you want to go backwards, you could. If we go forward, you can see, because we just did it. Can you guys hear me okay?
Mhm.
Okay. So 1/3 times 1/3, we know that's how we got each subsequent term. If we wanted to look at this idea just as review again, if you took any 2 consecutive terms and divided the rightmost one divided by the one right before it, you know, and reduce it or clean it up, we better get 1/3. That's the definition of a geometric ratio. This is 3 cubed, or it's say 9 times 3. Oh, I'm sorry. it's 27 times 1 over 27 times 3, and you would get 1/3. And that would happen for any of these. Of course, if we multiply by 1/3 going rightward, if we divide going leftward, we better get back to the 1/3. So that's what it means by common ratio, and that's the two different ways to think of what geometric is. When you move to the right, you multiply. If you move to the left, one term divided by the previous term, you better get the 1/3 as well. Okay. Any questions so far?
No.
Okay, so then now we're gonna look at, so now let's examine whether each of these sequences converge or diverge. So this is this initial discussion I was telling us that I think makes, in my mind at least, it makes all the difference in terms of what the majority of the next 5 sections are about. So we're getting there, okay? And this is the first thing we do. So a reminder of what geometric is. And by the way, it doesn't have to be geometric for what we are going to be doing all chapter, but it's just one example. And it's a simple one for us to look at. So that's why I'm picking it. And it is also part of this next section, 9.2. So anyway, so if we take the limit as n approaches infinity of the first sequence, and we could write it this way because we did not have a formula. I can show you what the formula is as well, but I would first just like for us to do it like this, just by logic. And well, how about I call the second one b sub n? So we have a distinction. And the limit as n approaches infinity of the second sequence, say b sub n. Okay, and they either, so as soon as we say a limit, then we know it's either going to converge or diverge. So those are the only two choices, okay? Remember, converging is what again, class? When a limit converges, it's because when we take the limit, we get a determinant value. And what are the possibilities for a determinant value again? So one of them is converging, and the other 3 is when the determining value we would get if it diverges. So the determinant, a determinant value when taking a limit So we're not talking about at this moment indeterminate, we're talking about determinate. When taking any limit, so is, so there's 4 of them, four determining values or determinant values. There's 4. 3 of them are, if you get any one of these 3, then the limit diverges. And when we get this other one is when the limit converges. So what happens when a limit converges? It's because we get what? What do we get when we take the limit? We get what kind of determinate value?
A finite numerical value.
We get a single, kind of being redundant, but finite numerical value. We can't get two numerical finite values or something. It has to be one. Okay. And I'm going to break this single finite number into two subgroups. Let's separate. Not a very equal separation. Let's separate this number one into two groups. Let's separate this single finite numerical value into two sets or groups. So let's separate this single finite numerical value into two sets. And sorry about the layout here, but my mind is just kind of going with where I feel it needs to go, and I don't necessarily think about where I'm drawing it. So anyway, let's say we call it, I don't know, some different notation for 1 and 2. So 1 is when you get, it's one kind of single finite numerical value, and that's when we get 0 only. You just get 0. That's a finite, single finite numerical value. So if we take the limit as n approaches infinity, any kind of limit, whether it's a sequence or it's just some formula in front of us, if we get 0, then that's part of this converging limit, and it's because it is a single finite numerical value. But now I want us to distinguish in our minds, oh, if we're looking at sequences and we get it to converge because it was a single finite numerical value, and not only did we get a single finite numerical value, but it was 0. And that's going to be a something special. That single number is going to tell us something that we're about to talk about. And then any other number is the other group. So it's not a very equal size group, because this is one single number and the rest is all the other real numbers. Any other real number except 0. So this is all leading to how I want, in my opinion, as your teacher, to organize these thoughts in our mind. And if we can get this part, then this chapter is really pretty nice. Okay. When we take a limit, whether we're talking about sequences or just anything, any formula, and if it diverges, we know that it diverges because of when you get done taking the limit, something happens, and it must not be this single finite numerical value, because otherwise we would have said it converges. So of course, what are those possibilities. What could we get? And we would say the limit diverges. What was one of them?
Infinity.
Infinity only. And the other one?
Negative infinity.
And this strange one that happens, the fourth one?
It's the oscillating or alternating.
Oscillating, or we can say alternating. Alternating behavior. That is not getting closer to any single finite number, because if it was, there are oscillating or alternating types that do oscillate, or they alternate positive to negative, positive to negative. They don't even have to be positive to negative. It could, but it could be a positive and a positive, like 2 and 2, 4, 2, 4, 2, 4. Oops, you can't see. So I wasn't drawing much anyway, but see, that's a 2, and then the next term's a 4, and the next term's back to a 2 and a 4, like that. These are alternating, but they're not alternating and getting closer. They don't have this behavior that's it's not getting closer to any single finite number. So we have to be a little more, I'm not criticizing or anything, I'm just saying we've got to make sure that when we think of this oscillating or alternating behavior, it's one where the oscillation, or in this case alternating, because they're single dots, they're single terms, versus a function that's continuous and alternating like a curve. That's when we think of oscillating, and when they're just terms, we think of alternating. And alternating behavior that is not getting closer to any single finite number. Okay, so this are the three types that we, if we get any one of these three, then we have determined, it does determine the value of the limit. It's just that it's a divergent type, yeah. And there is an alternating type we talked about this in the last section. We could have, say whatever, say this is a 2, and you have alternating, this is the y-axis, and just say, I'm just making one up, it could be alternating on both sides, a little below 2, a little above 2, but they're getting closer and closer to 2 as you go out forever. So then this that's not this number 4 here. That would be, even though it's alternating closer and closer to a single finite value. And so that would be this up here, which is a converging type of alternating. The other more famous one that alternates, or if we talk about sequences, if it alternates on positive and negativeness, and also getting closer and closer to 0. And that also is not this type right here, but it's this one up here. And then if it gets closer to 0 again, then we're supposed to be, now that's going to tell us something. That's the next thing I'm about to talk about, is it's this special subset of number 1 over here, or which is when you get a single finite numerical value and you get 0 only. But I mean only, I mean not any other number. So maybe, I don't know, that could be ambiguous or confusing right here. you just get 0. And this is when you get any other single finite, any other single real number except 0. Because otherwise it wouldn't converge. If you get more than 2 finite numbers for the limit, well, then that would be one of these down here or something. Okay. All right. You probably like, what the heck am I talking about? And you don't know where this is going yet, but any questions, at least what I'm saying so far?
No.
No.
Everybody's okay? All right. So now let's go back. We talked about what's determinant value or determining value when we take a limit, whether it's a sequence or it's just some equation. And now let's take so even though we don't have a formula and we're not physically taking a limit, we can also take a sort of a informal guesstimate, if you will, about the sequence by just looking at the terms. So what about the difference between these two sequences, which happen to be, I just picked them on purpose to be geometric sequences on top as well. So what's happening to these terms here, of course? Are they, which one of these types of determinant value is it here? Are the terms getting closer and closer to a single finite number as we go out? Well, if it is, well, then that's this category, which is a single finite numerical value, which means the limit converges, or we can say the sequence converges towards a single finite number. Or is it a diverging limit, or which means a diverging sequence, because one of these three things happen. So, Jocelyn, what do you think here? 2, 6, 18, and so forth. What's happening to these terms? Even though we don't have a formula, we can still tell by just observation which one of those is going on there.
It's approaching infinity.
Very good. Yeah. So this would be going to infinity. And we would write that here. And this is by observation, not by actually mathematically taking a limit, but we could also do that. By the way, the formula for this one happens to be, without really getting into how that is, but it turns out to be okay. And so the formula for this one on top, if we tried, if you put, and this would be for, and by the way, that reminds me that there's a notation for, but I'll wait on that. So this is starting at n equals 0. Starting at, well, I can make it up, I guess, so that it doesn't start, because I already wrote 1 here. So, sorry. So let's say n minus 1. Okay. So, you can't see both. So, be patient here. We're I don't know, 5-10 minutes away from having this initial discussion done. Probably more like 10. But anyway, if we put a 1 right here, if I wrote this formula correctly, it should give us this term and so forth. So if we start at 1, n equals 1, then if we plug 1 right here, well, 1 minus 1 is 0, 3 to the 0 is 1, times 2 is the 2. If we put a 2 in, well, then we better get a 6. So put a 2 right here, 2 minus 1 is 1, 3 to the first power is 3, 3 times 2 is 6, and so forth. So And by the way, because it's geometric, all geometric, I'm gonna wait on that. So, okay, let's just take the limit. If we physically take the limit instead of by observation, we still better get infinity. Yeah, and if you do put infinity right here, of course, n approaches infinity. Infinity minus 1 is still infinity. 3 to the infinity means 3 times 3 times 3 times 3 times 3 forever. That's still infinity. Times 2 is still infinity. So either way, by observation or by, if we had the formula, which we just wrote down, we would get infinity. And these are the same, and therefore the limit diverges because it's this type. And we also can say, therefore, the sequence diverges. Okay, any questions here?
How do we get the formula 2 times 3 and to the n minus 1? Where do we get that from?
Yeah, that's a good question. At this one moment of time, I'm going to delay your question.
Okay.
And because we will answer, I will answer that in a moment. But
All right.
I wanna, when I do answer it, the reason I paused, I was about to write it, is because normally when you have a geometric sequence, for whatever reason, authors like to start it at 0. And then I would have had to go back up here and change this. So
Okay.
I didn't want to confuse you unnecessarily. So I just knew, how do I say it? I knew, I know how to write it just based on experience that this would work.
Okay.
And I am going to tell you, but I'm going to tell you for a geometric sequence when we don't start at n equals 1, but when we start at n equals 0.
Okay.
And speaking of that, I guess since you raised the question, I will write it down right here. All geometric sequences, and I can actually answer your question as well. And usually, because we will need to know that what you just asked for the problems on this section. So it's a good question. I just didn't know if what was the right moment to talk about it. But anyway, all geometric sequences with a sub 1, no. They just call it A, and it's either going to be A sub 1 or A sub 0. It just depends on how we define it. But with A being the first term, or I'll say the beginning term, that might take away some ambiguity here, confusion. With A being the beginning term and R and common ratio R. Can be written by using A sub n or B sub n or whatever equals the beginning term A times the common ratio R to the nth power for n starting at 0.
Is that a and between term and common?
Between term and common. Yes, that's an and.
Okay, cool. Okay.
Sorry.
Okay.
For n starting at 0, or we can say n equals 0, would be the beginning term. Oh, yeah. And, or these can be just manipulated. If you don't want to start at n equals 0, like what did I start up here at? We started not at n equals 0, but n equals what?
1.
1. And then there's just a little alteration needed. It's still, the beginning term is still going to be called A. Common ratio is still R, just that the exponent gets shifted and you would have to subtract 1. And this is for n starting at 1. And these are the two most popular that we'll see. You probably won't even see it. Well, you could. But if it is starting at 2 or something, then they usually just give it to you, the formula, instead of ask you to come up with it. So I did, thank you for asking the question. We did need to talk about that as well. And we were going to, I just didn't know if that was the right moment. But since you asked, see, what did I write right here then, Denise, for this sequence? Which one of these two is it right here? The first one right here or the second one when we started at n equals 1?
You wrote the second one.
Yeah. So what have we written? A sub n equals, what was our beginning term?
2.
2, which we wrote right here.
Mm-hmm.
Times,
common ratio.
which what was our common ratio?
3.
3. And then raised to the what power?
1.
Well, what's this expression right here?
Oh yeah, yeah, 0.
I mean, oh, can you guys see this right here? Can you see my pencil? So the whole general formula, you're right. This one was, the beginning term was when n equals 1. And then we went to n equals 2. That's correct. And that's why you knew to use this formula down here instead of this one right above it.
Mm-hmm.
But what do we, when we actually write the formula, A was 2, our common ratio 3 raised to what expression in the exponent position, then it's either n or n minus 1. And how do we know which one to pick? Well, it depends where you start at, right?
Okay.
So if we start at n equals 1, then what are we always going to put right up here? And when we write the general formula of that geometric sequence, are we going to write n or n minus 1? If we start at n equals 1, we're always going to write n minus 1.
Okay.
Which is what I wrote right here. N minus 1. Okay.
Okay.
Somehow I lost you right there.
A little.
So this has a formula. Right? There's a formula we can always write when it's geometric. Yeah. And for our purposes of this course, if we're ever asked to write one ourselves, it's going to be like 99% sure they're either going to say, hey, start when n equals 1, or start when n equals what?
0.
If they start with n equals 0, that would be like this. N equals 0. So this would be a sub 0 And then I'll just make up a number. Say it was 5. And then the next term would be when n equals 1. And that, let's just pretend that this was 5 over 4. And so forth. And this would be a sub 2, and then this would be 5 over 16.
Mm-hmm.
So in this case, if we were asked to write the formula, we would say sub n equals which one of these are we using when starting at n equals 1, or did we pick when starting with n equals 0?
N equals 0.
So that means we have to use this one right here, huh?
Okay, yeah.
And what would we write? A sub n equals, and what's our beginning term here, Denise?
5.
5 times the common ratio r, which we haven't written down yet, but we can figure it out. And what would we write up here in the exponent position? What expression? It's either n or n minus 1. And which one do we use?
N?
N. And good. Now the common ratio, either you notice the pattern by moving rightward, and if you notice the pattern, then you just write it down. If you don't notice the pattern and we are told it's geometric, then you just pick a term divided by the previous term and reduce it, and then that'll give you the common ratio.
Okay.
Yeah, like I did way up here, like we did up here.
Mm-hmm.
Right here. So can you see what that would be, Denise? If we can't, then we go backwards and we take a term and we divide it by the one before it.
Okay.
Or if we can see it by moving rightward, then we just write it down.
Okay, so would R be 1/4?
Good. So here we would put a 1/4. And this would be the formula for this geometric sequence. And the one I wrote up here was this one. And the reason it has an n minus 1 is because I just picked the sequence to start at n equals 1. Okay?
Oh.
Does that make sense?
Yeah, much more sense.
Okay. Anyone else have a question there?
No.
No? Okay. So going back to this now, can you guys see this okay? I know it's smaller, but is it readable?
I can read it.
You guys are okay?
Yeah.
Okay. I'm not going to always stay with this, but maybe just for the next few minutes here. So what did we say was happening to these terms of this geometric sequence when the common ratio was 3? What, by observation and also by actually taking the limit of the formula, which now we understand how the formula came about. So either way, what are these terms doing as they go out forever and ever? Which one of these determinant values is it? It was not the converging type, but the diverging type, and it was the infinity. Yeah?
Yes.
Everybody okay with that?
Yes.
Okay. Now, what about this one? The second geometric sequence, or just, it is geometric, so, okay. So what about this one? Now, maybe I can squeeze it up here. And what happens if we take the limit as n approaches infinity of b sub n, and that's just the notation for all of it, this whole thing, and by observation. And this is by observation again. By observation, and then we also could do it if we had the formula. So I know this is small. Okay, so by observation, 1, 1/3, 1/9, 1/27, 1/81, doesn't the denominator, the numerator stays 1, and the denominator just keeps getting bigger and bigger times 1/3. But, or you can just say the denominator is getting bigger times 3, either way. So what's happening? All of these are getting, as you go out, the numerator is still staying at 1, but the bottom is getting bigger and bigger. So what happens by observation? These numbers here are what? Getting closer, and are we able to determine a value by just observing? If not, we can write the formula down and do it computationally. But what do you guys think? Joshua, what do you think? What do you think's what does the pattern look like here as we go out forever?
It just gets closer and closer to 0.
Very good. So it's this type, huh? This determinant type, a single finite numerical value,
Yes.
which means that the limit converges, which also means the sequence converges towards 0, huh?
Yes.
Okay, good. So we can put here 0, which means converges. And now that is supposed to trigger another new little red flag in our mind, and says that this converging single finite numerical value, I want our minds to start thinking that, oh, it's which one of these subsets of a single finite numerical value is it? It's the 0 type, isn't it?
Mm-hmm.
It's not any other single real number except 0. We didn't get 3 or 7 or -2. We got 0. Yeah. And that's
So
going to tell.
sorry, I'm sorry, I was a little lost. So for b sub n, we found the limit by just observation, right? We didn't actually compute it.
Correct.
Okay.
So now we could also compute it, Denise. You keep in your mind keeps saying, okay, what are we going to do next? And then you keep asking. So you must be clairvoyant or something. So what's going to be the formula for b sub n? Because it's geometric, and we have this down here. And if it starts at n equals 0, or if it starts at n equals 1, we can write it by looking at either one. By the way, if it started at n equals 2, take a wild guess what's going to go right here. N minus
2.
2. Okay?
Okay.
Like that. There's always ways for them to manipulate it, but you don't need to get anything, you don't need to worry about anything other than these two. Okay? You'll be fine.
Okay.
So what would be the formula then? What would be the formula, Josh, then for this b sub n right here if we use the correct one over here? And we're starting at n equals 1, so we're going to use this one again right here. Okay? So what would we write? What's A stand for?
A is going to be 1.
Good. The beginning term. Times?
1/3.
Good. Raised to what power?
N minus 1.
Mm-hmm. And then do we really need to write the times 1, Joshua?
No.
What would have this formula been if we started at n equals 0, Joshua, instead?
It would have been,
Well, just pretend that this would have been a 0 and there's still a 1, right? Just pretend. So then it would have been just what?
1.
1 times 1/3 to the what power?
It would have just been 0.
But what do we have to, because it's not always going to be 0, it's going to keep changing as we move out to every term. So would we write n minus 1 or just n if the first term, the beginning term was at n equals 0, and they told us it was n equals 0 instead of n equals 1.
It
Yeah.
would just be n.
Yeah, is that okay?
Yes.
Now, what would happen if we took the limit by computation, which Denise was just asking about? We better get the same answer as by observation. Yeah.
Mhm.
And this right now, it's kind of confusing how it's written. Because if you, oh, well, I don't know. What happens if you put infinity right here? Joshua, what's infinity minus 1?
So infinity.
1/3 to the infinity power. So that
Infinity.
means 1/3 times 1/3 times 1/3 times 1/3 times 1/3 times 1/3 forever. That's one way to answer this question of doing it computationally. Another way, by the way, what would that be, Joshua? What happens if you keep multiplying 1/3 times 1/3 times 1/3 times 1/3? The answer keeps getting what? Maybe that's kind of hard to see in your mind.
Could you hear me?
No, I didn't hear you. Did you say something?
Yeah, it gets smaller and smaller.
Oh, okay. So smaller and smaller to what?
Towards 0.
Yeah. Now, if that doesn't feel comfortable to someone, then you'd have to rewrite this little piece and to make it more comfortable. And I just don't have any space here. I'm just gonna squeeze it up here. Sorry. Limit as n approaches infinity of. Another way to write this right here is to go like this. We don't really need the 1 in front. And we could split this up as 1/3 n minus 1 n minus 1. I don't like that. I'm just going to put 1 on top. Because as you go out, 1 times 1 times 1 times 1 is 1. So we can just say 1/3 to the n minus 1. So this right here, before you take the limit, 1/3 to the n minus 1 is the same thing as 1/3 to the n minus 1. Because what's in the numerator of all of these fractions?
1.
1. So that's what that is. And in the denominator, if you put a 1 right there, 1 minus 1 is 0, 3 to the 0 is 1, you get 1/1, and that was this first term. If you put a 2 right here, that should give us the next term. 2 minus 1 is 1, 3 to the first power is 3, and you get 1/3, and so forth. So I hope you can see that this, and I'm glad that we're talking about it because that does cause potential confusion and when we're doing our homework as well. So if you ever have like a 1 on top and it's to a power, n minus 1 or n, you can, if it's worthwhile, if there's a good reason to do it, so you can rewrite it like this, 1/3 to the n minus 1.
Okay.
Is that okay?
Yes.
Now, why would that be sometimes worthwhile? Because this exact moment when we try to compute the limit as n approaches infinity and put infinity right here, we got 1/3 to the infinity minus 1 is infinity, 1/3 to the infinity, and we're like, what is that? So if we're comfortable with that, then we don't need to rewrite it. Because Josh already said it was getting smaller and smaller because he was either he did it mentally in his mind and realized it was getting smaller and smaller, or he just kind of looked up here and the same thing, these terms are all getting smaller and smaller. Or if that doesn't feel comfortable to a person, then they can do this instead, change this 1/3 to the n minus 1 and write it as 1 over 3 to the n minus 1, because that is equivalent to all this. So now what happens when you take the limit? Now you have 1 on top, and what's going to be in the bottom? Infinity minus 1 is infinity. 3 to the infinity is getting larger and larger. And what happens when you get 1 over a larger and larger and larger and larger number? It gets closer and closer to what?
0.
0. So do you see how we can change this? If we take the limit and we're a little uncomfortable, and we could always change it to this, which then is a more obvious way to compute and realize that the limit is 0 through computation. Does that make sense?
Yes.
Okay. So far, so good, Joshua?
Yes.
That was a dragged out yes.
It comes and goes.
Okay. So so now we're ready. Oh, so again, what did we get? The limit converges to 0, which is this one right here, the single finite numerical value, but it's the subset of this. We broke it into 2 subsets, and it was this one right here. And this one, well, both of them they tell us some extra information that we're about to need in a few moments, okay? So when we look at any sequence, even if it's not a geometric one, and we look at the sequence and we want to ask, hey, what's going on to these terms as you go out forever? Are they converging or are they diverging? That's one interesting thing that we can explore and be curious about and want to know. Or even if we're not curious and we don't want to know, it might be a homework problem for us to learn, okay? So that's one area of curiosity or area of exploration or homework problem that we might be asked to do, and we are being asked to do. But now we're going to extend this exploration into another an idea, a topic that involves these terms of these sequences. So now we're going to consider. So the first thing we want to do when we're asked about a sequence, we're going to look at if the sequence itself converges or diverges. And if we do get an indeterminate when we take the limit computationally, if it's unfriendly, then we have to manipulate it into friendly, use L'Hopital's, or in some cases, I'll just leave it at that. And then we'll get a determinant value, and it'll be one of these 4 right here. If it's diverges, well, then that was because of one of these 3, and we're done. The sequence diverges, the limit diverges, so the sequence diverges, and we will know because of which one of these 3 reasons. If it converges, then I want us to be thinking about which subset, yeah? And then that's going to tell us something. And now we're going to talk about what is that something. So that something is, let's do another thought. Let's bring in another discussion to the table. And that is, what if we were interested in what happens if you start to add these terms up? Yeah? Forever. So what would happen when we start to add these up on this one? Well, 2 plus 6, is 8, plus 18, and so forth. So if I'm just going to switch to decimals. I mean, we could sort of answer it by just looking at it, but by the way, on your computer monitor, do you only see the notebook or do you see anything else?
I just see your notebook.
Okay. And nothing else. Do you see participants? Do you see WebAssign? You don't see anything else?
Nope.
Just your notebook.
Okay. And now when I click this, now you just see WebAssign?
Mm-hmm.
Okay. And now I click this, you just see Desmos, right?
Mm-hmm.
Okay. So, just needing a calculator here. Well, I'm going to do, yeah, so just using a calculator, what happens if we start to add up the terms of that sequence that was on our paper? So the first term was what? What was
2,
2 plus
6.
and so forth. Oh, so a lot of initial discussion here. So again, if we understand all this well, then the rest of the next 5 sections are really pretty nice. And most of them are really nice. There's just some that are a little messy algebraically, but that's it, but not that messy. Anyway, so this was the first term. This was a sub 1. Yeah. And we are going to analyze, because we're curious people, and we're going to analyze the sum of these terms. So be patient, stay focused, because now it's the last part, but it's critical that we understand what we're about to say. Analyze the sum of these terms as we go out forever. This sum will have a determining value or a determining limit value as well. This is another discussion about a limit value other than the sequence itself. Because we already said this was a 2, a 6, an 18, a 54, and so forth, 162, and this goes out forever. And we already said that one exploration of curiosity is if you want to be curious about the limit as n approaches infinity of the individual terms of this sequence. And that's what this is. And that's what we were just talking about. And we did it 2 ways, one by observation and one by computation from the formula. And in either case, we got we got infinity, which diverges. Yeah?
Mm-hmm.
That's one discussion of a limit discussion that we can explore, and we must explore it. But now we're asking about a different determining limit value as well. It's a separate question. It's in a separate exploration, curiosity, question on WebAssign. And that is not just look at what happens to these terms individually as they go out forever, which was this part, but what is the sum of these terms doing as we go out forever? So the sum of the terms, which I already wrote here. So there's something for sum, we say S sub 1. That means the sum of just the first term. S sub 2 means the sum of the first two terms. So here is our second curiosity topic, forever. And then question, does this sum converge or diverge? And as soon as we say anything about a limit, then we want to get the determining value. And it's those four things again. But it's these four things from the notebook: single finite numerical value, which is the converging type, infinity only, negative infinity only, oscillating, but not in terms of this limit question that we already were curious about and already finished and answered, but about a new topic that still involves this sequence up here, but it's not looking at the individual terms as you go out forever. We already analyzed that. Now we want to analyze what happens when you start to add them up forever. That's another separate limiting question that we're curious about. Okay? So, and we're either going to get they converge. When we start adding these up forever, they're going to converge to something, which means a single finite numerical value, or they're going to diverge. And diverge means three possibilities again. The diverge was infinity only, negative infinity only, or the alternating type without me writing everything down again. And this converge was to a single finite number. So one of the biggest confusions that we have when we're learning this topic is that they get this idea, this limiting question confused with this one up here. And they think they're the same, or they get mixed up and they think, oh, are you asking about this question or this question? Because it sounds similar and you're using the same sequence to explore your two curiosity topics. One, the individual terms as they go out forever, converging or diverging, which again, as soon as you ask about limiting any limit of any topic, well, then it's either going to be converging or diverging. Converging is this possibility. Diverging are these three. So any single time we're ever asked about a limiting value question, once we have determined the value of the limit, then it's one of these two every single time. Converge or diverge. Converge is this, which means this, single finite numerical value. Diverge means one of these three. So whether we're being asked about the limiting value of the individual terms, we're gonna get one of either this one or this one down here. And if we do get single finite, then we're supposed to think about those two separate cases, 0 and any other number. But that's when and that's only necessary for our brains, our minds, any other not equal to 0 here, without me trying to write it all out. We only need to think about this subset of the single finite numerical value when we're exploring this one, this curiosity question, this limiting question. Because because if we do get converges when we're exploring this first topic, this first question, if we get a single finite number and we write converges, then we want to also extend it into which one of these subsets of single finite number. Is it the 0 or some other number, single finite number? And because if it's this one, or this one, it's going to answer partially or completely this topic that we're looking at on the second curiosity. So, well, let's talk about this second limiting topic or curiosity or question from WebAssign. So what is the first sum? And these are called partial because we're not adding all of them up, all the terms. We're only adding up a few. And in this first case, we're only looking at the first term. So this means the first partial sum is just the most simplistic sum of all. It's just the first term. We haven't gotten anywhere yet. So that's a 2. What about the second partial sum? That would mean we now are looking at the sum of not just the first term, but the first 2. So this one plus this one, this part is the S sub 2. So it's 2 plus 6, which of course is 8. So hang in there. You guys, hope you're hanging in there. And what about S sub 3? What's S sub 3 then mean, Joshua? It means we're going to look at the sequence up here, but add how many, not all the terms forever. That's our eventually that's what we're interested in, but we're just trying to observe and see if we can see a pattern here. So what's the third partial sum mean, Joshua? It means to add what?
18.
I'm sorry?
Means to add 18 to the first 2 terms.
Good. So it's 2 plus 6 plus 18. So 2 plus 6 plus 18, or you said you could just add 18 to the previous answer and whatever that is. So that's 26. Okay, so hang in there. What do we want to know? What happens when we keep doing this forever? Which is a limiting question. And as soon as we say, oh, it's a limiting question, then that means it's one of these, converging or diverging. And that's what we want to find out. So, Denise, let's just go one more term. What would be S sub 4, that's the fourth partial sum, which means add up the first what?
The first 4 terms.
Mm-hmm. So that's the 2 plus the 6. If we wanted to go faster, we could just say, well, we already know the first 3 is 26, and then just add what?
54.
Mm-hmm. So either way. And whatever that adds up to. And then we start to get an idea by observing only. Right now, we're just doing the observing part, and then we'll also learn what are the next 5 sections about, how to figure out this question of interest right here, but not by observation, but by computation. And by computation, there's like 7, I don't know, there's 9 or something techniques that we have to learn that all do, well, they all try to do the same thing, which is to do this part right here. What happens when you start to add them up forever? What kind of determining limiting value do we get? Converging, diverging. So, oh, and by the way, this adds up to whatever that is, 80?
90.
90? Okay. Let's see, 54 and 26. Is that 80? I think that's 80, isn't
That's
it?
80.
Oops, my bad.
It's okay. I was gonna say 40 a moment before that, so I was even worse off. Okay. So what does it look like by observation? If we keep adding, the next term would be S sub 5, and that would be 1, 2, 3, 4, 5, and now you would add, you would be on this number from before, plus another 162, and that answer is going to get bigger yet, isn't it? Does that make sense?
Yes.
So what do you guys think in terms of observation and your intuition, your logic? What do you think you're going to say about this, the sum of these terms added up as we go out forever? What kind of determining limit value will it have? As soon as you say limiting value, it's either converging or diverging. And if it's conversion, it's because of single finite number. And by the way, when you get to the second limiting question, you don't need to worry about these 2 groups. You just need to worry about, I get a single finite number only. It doesn't matter which one of these. That's only for the first limiting value curiosity question. Okay, so what do you think, either one of you? You think we're going to get closer and closer to a single finite number if we keep doing this forever and ever and ever?
No.
Or do you think we're going to get a diverging type, which would be one of these 3 right here? What do you guys think?
Diverging.
Huh?
Diverging?
Diverging. Josh?
Diverging.
And which one of these diverging?
Infinity.
Very good. Yeah. So you're correct. It's going to diverge. The sum of these terms added up forever are going to diverge, and specifically diverge to infinity. Yeah. And great. Now, so we're getting closer and closer here. So what we just answered is, so let me tell you about sum. Summation, there's this Greek capital letter, uppercase notation for S in Greek is this. It's called sigma, uppercase sigma. That's a heck of a name for a letter in the alphabet. So instead of saying S, we keep it simple. We just say S because it sounds like, it looks like, well, our minds were trained that way when we learned our language. And we said, oh, well, that's an S. And when they were trained and I don't really know how this works. I mean, how the heck do they read with these letters? I don't know much about languages, okay? I don't know anything, but so I'm kind of confused. Why would they just say sigma when they were doing their alphabet? I don't know. But anyway, that's a separate question. But and then you would say summate the terms of the sequence. Oops. And oh, that's pretty horrible. Anyway, it's supposed to be a brace like that. And then a sub n in it. And then you have this sigma in front. So ignore this part. And it would be from starting at either n equals, what are the two most common beginning place values for n, Denise? Either
0 or 1.
Yep. And what did we do way back 500 years ago when we started this lesson? We called this one n equals what?
1.
1. And we want to go forever. So what's forever? When n goes to what?
Infinity.
But when you read an author, they never write n equals infinity. They just leave this part out and they just write infinity. But that's what it, for whatever reason, just like in antiderivatives, do authors tend to write, just pretend, do authors tend to write here at x equals 0 and at x equals 2, or do they leave it blank? Don't they leave it separate? Don't they just not write that down? And same thing, like there's all kinds of little oddities. When you have when you have a root and there's nothing written here, what are we supposed to know is there?
A 2.
A 2, and they don't write it down. Why? I don't know. Same thing here, and same thing here. When they don't write anything, when they don't write n equals infinity or n equals whatever, they just don't bother to write it down. But that's what we're supposed to know. Okay?
Okay.
Okay. So when we see this, that looks pretty horrible there. But when we see this, we're supposed to know, I hope, from this moment on, what the heck is that they're asking us? They're saying, hey, take us, this stands for a sequence, right? Which means it has an infinite amount of terms. It might start at n equals 1 or n equals 0. Well, it tells you right here. Oh, they decided to say the first beginning term. I should say the beginning term is at n equals 1 instead of n equals 0 or n equals 2 or n equals 5, whatever. And then this says to us, hey, add them up forever. Not stop at the 99th term or the 4th term, but go forever. And as soon as you see this, we're supposed to think, oh, this is a limiting question. This is a limiting question, which means we need to figure out the determining limit value, which means it's either converge or diverge, which means it's either a single finite number or one of these three diverging determinant values. And then we're supposed to also think, but which kind of limiting question are we being asked to analyze when it says this part versus this part? So this is one limiting value question, and this is another one. Well, which one is this one, and which one? Well, I'm down here, so obviously this one is the second question. When you're analyzing the sum of these terms as we go out forever, this is asking the first curiosity we had about limiting value, which is the individual terms as they go out forever. That's what this is. So it's very natural for us to get confused about all this. And when students read this or read this, they don't really, maybe it's hard for them to realize that it's two separate ideas, two separate topics. Okay? Am I losing you guys?
No.
Denise, are you lost? You're exhausted? You're falling
No,
asleep?
no, I tend to understand things better when we're actually doing it. So I'm sure I'll get it when we practice.
Okay. Yeah, so I know, and I get long-winded here, but it's really, I just know from experience that you talk to most students who go through Calculus 2, and even though they do this chapter, they're not really understanding what this is all about. They're just kind of
Okay.
question. So that's what I try to emphasize, but I can understand how it can get just kind of like, it just seems like a bunch of stuff here. But anyway, so when we're asked this question, we're supposed to realize what? Are they asking us what the determining limiting value is for the sum of the terms of a sequence, or just the individual terms? What's this
Individual.
one? And what can happen with any limiting question? We can either get what? So this right up here, when we get the determining value, it can either converge or what?
Diverge.
And if it's this first question about the individual terms of the sequence, if we do get a single finite number, which means it converges, then we're supposed to, I want us to think, oh, but which one of these subset of single finite number is it? Is it the 0 or any other finite single number? Because if it's depending on which one it is, it tells us something about this answer. Okay? Okay. So what kind of answer did we just get for this one up here? Which is
Infinity.
this question. We got infinity, which is diverges, right? And it's of the diverges, that's this one. Therefore, we are like, wow, thank you very much, because now I already know what's going to happen with this one. If we ask this limiting value question, analyze the sum of these terms as we go out forever, we know now, without even having to think about it very much, that because these numbers are getting bigger and bigger, diverging to infinity, when you start to add them up forever, which is the second topic of interest, then this sum, there's no way it's going to converge towards a single finite number. And you guys already observed that right here. The sum of these terms were getting bigger and bigger forever, weren't they?
Yes.
And we said what? Oh, I didn't write it down, but what do we know about this? So we see this and we say, oh, this means we're now being asked, what's the limiting value? What's the limiting determining value when you start to add these terms up forever? Is it converging? Is it diverging? Well, if it's converging, it's getting closer to a some single finite value, numerical value, or it's diverging, which is one of these three. Well, what did we already realize when you start to add these up forever? Are they getting closer and closer to a single finite number, or are they just getting bigger and bigger?
Bigger and bigger.
And so this one has to this one is infinity, which means diverges. which means when you add these terms up forever, they never get closer and closer to a single finite number. They just keep getting bigger and bigger, positively speaking, not negatively speaking, or the sums. This would mean the alternate part would mean when you keep adding these up, you add one term and it gets bigger, and then you add the next term and it gets smaller, and you add the next term and it gets bigger and smaller. And that's when these are alternating like positive and negatives, possibly. So the interesting part is this, to converge, the second interesting limiting value question, the only way it can converge, the only way the sum of these terms, well, I'm like 4 or 5 minutes ahead of myself. So I want to go to the second sequence, and then after we do this, then we can work on the homework. Okay, so yeah. Okay, what about the second sequence from our notebook? What was that one? That was 1, and then it was what? 1/3, and then it was 1/9. Remember this one?
Mm-hmm.
Forever. So it's going to start to come together now very quickly. So we have 2 types of limiting value questions that we are going to be interested in for this chapter. One is this first limiting question. So, first question. What's the limiting value? What's the limiting determining value as you go out forever of just the individual terms of the sequence? And how can any limit value be answered? Either with observation or with computation. Right now, we're just doing it by observation, but on the notes, we did it both ways because we wrote a formula down. But for right now, in this discussion phase, what did we say, class? What did we say here? That these individual terms were doing what? Were they converging? Were they diverging? If it's diverging, it's one of these 3. Or was it converging, a single finite number? And if it was, because it's the first question, limiting question, it helps us if we know which one of these 2, the subset type. But what did we say these individual terms were doing? They were what? Converging?
Converging.
0.
And what does converging mean then? That means to a single finite number?
Mm-hmm.
And what single finite number was it converging to? Converges towards what?
0.
0. And did we answered that in the note page, both observationally and by computation, and we got 0. Okay.
Mm-hmm.
So now, okay. So the second the second limiting value question they could ask us is, what is as you start at n equals 1 or 0 and go forever to infinity? They're not going to write n equals infinity, but I just wrote it there, of this sequence. And they could write it in this form without writing the formula down, or they will have the formula right here, which was that that 1 times 1/3 to the n minus 1 power. So that's what we'll also see. They could have written down that. Right in here, they could have written the 1/3 or the 1/3 to the n minus 1. And that could have been put inside, right? Well, if you do that, then you don't write brace anymore. So if they did, they could also write it this way. Or and we also remember this was the same as 1/3 to the n minus 1. Well, anyway, so this is the same question as this one. It just on this one, they put the formula in, and this one, they're not. But either way, they're the same question, and it's this second question that we are curious about, which is the sum of all of these, not the individual terms. That was the first limiting value question, but the second one is the sum of all these as you go out forever. So this is either going to be converging or diverging again, because it's a limiting question. Therefore, the determinant, it has to be either the converging or the diverging. Now, so the only chance, it's difficult to get converging here. It's a tough challenge for the sum of the terms of a sequence to, when you add them up forever, it's difficult to get this converging to a single finite value. It's a difficult challenge for that to converge. And which means well, I don't want to say most of the time, but we get diverges a lot. Now we're going to have homework problems where they converge, but the only chance for this sum, this second limiting value question, the only chance that it can ever converge, and we're almost there, is when the first question, the individual terms get closer and closer to 0, which is the converging to a single finite number, but it's this case right here, when it's to the 0 one. When the only way this second limiting question will ever converge, the only chance it'll ever have to converge for these terms to add up, when you add them up forever, for it to converge to a single finite number, is when the individual terms, as you go out for and ever, which is the first question, converges, but to this special case right here. If it's anything else, well then the second question will diverge every single time. So if you get this question right here, and you look at the first limiting question, the limiting determinant question about the individual terms, and what did we say these individual terms were doing? What was the determining limiting value? Which one of these two? It was what? These terms did what? Converge or diverge?
Diverge.
And so as soon as you get this, you're like, oh, thank you very much, because now if they ask me about the second limiting question, which are the sum of these individual terms, there is no chance whatsoever for the sum of these individual terms to converge. And you just write right away, you write diverges and you're done.
And that's always?
Always. Always.
Okay, so whenever the limit diverges, your
Which
sum,
limit? Which limit?
the individual limit,
Correct.
the sum will also diverge.
Every single time.
Okay.
Not only that, Denise, but when this right here, the individual terms converge, how many subsets did I try to tell you guys to think about when you get the first question, the individual terms, and they converge? I'm asking you to think about it in how many subsets?
2.
If you get this one, then the second question is also done already.
Mm-hmm.
It diverges, the second one, the sum of all the terms.
Mm-hmm.
So when is the only time this second question of interest, this limiting question, when is the only opportunity for this to ever converge? Because it's difficult. When is the only time it even has a chance to converge? It's when the first question, the individual terms, what? Converge to a single finite number, but they have to converge to what single finite number?
0.
0. And then you're like, oh, shucks, because now the second question, which is the sum of all these terms, it could converge or it may diverge, and we don't know yet. And then we need further exploration, which is all the rest of the chapter, when we have to learn what tests we can do when we get this case right here for the first question. Because if this first question, the individual terms, if they diverge, well, then we're done. That means the second one diverges. Done. If the first question about the individual terms converges to a single finite number, but it's not 0, it's some other number, single finite number, will you still say this first one converges? Because it does. But the second question about the sum of the individual terms forever, it's impossible for that to converge if you got this answer for the first question. The only chance that this ever, the sum of the individual terms, when you add them up forever, the only way it can ever converge, which is extremely difficult, is if the individual terms converge to a single finite number, but converges towards what?
0.
And then we're not done yet with the second question. We're done with the first question, but we're not done with the second question. And then that's when we have to explore further. Now that either made sense or it's or not, but I hope I'm gonna keep referring that now. So then guys, what happened with this first question right here on this sequence? What happens to the individual terms, which is the first question? Which one of these is it? Diverging, converging? The first question, just the individual terms. They were what?
Converging.
Diverging?
The first question.
Converging, yeah.
Towards what?
0.
Which one right here? Yeah? Isn't it this one?
Mm-hmm.
Which means then, oops, that means when you add these terms up forever, there's a chance that when you add these up forever, it could converge. We don't know yet. And we need to do further exploration. So this one right here, because we got 0 for this first question about the individual terms, then we're not done. We're not done answering. We cannot automatically say the second question diverges. We don't know yet. It still might, but it might not. So when will this diverge? This diverges almost every situation. And when will it diverge? The sum of these infinite terms. So when you answer the first question, as long as you don't get what answer? As long as you don't get what answer?
0.
Then if you don't get 0, then this second question diverges every single time.
Okay.
If you do get 0 for the first question, then we pause and then we say this second question could converge, it could still diverge. And we need to do further mathematics to find out which one it is. And that's what all those tests are that we're going to learn starting with 9.2. Okay, but 9.2, well, I'll just leave it at that. So, any questions there?
So
No.
this one doesn't converge?
This one?
Yeah.
Well, the individual terms converge, don't they?
Mm-hmm.
And they get closer and closer to what? What kind of single finite number?
0.
0. So what does that tell us then about the second question? When we want to analyze the determining limiting value for adding them up forever, we don't know yet if these add up closer and closer to some single finite number or they don't. We don't know yet. Either one's possible. So then we have to do more work to find out if the sum of all these terms converges towards a single finite number or not. Okay?
Mm-hmm.
Okay. So by the way, what would happen if we start to add these up forever? Let's let Desmos do that. So I need to erase this part. And so help us out here, Denise. What's going to be the first term of this sequence, which we know has a chance when you add these up forever? Hey, because these individually got closer and closer to 0, which meant converges towards 0, then there's a chance when you add them up forever for it to converge towards some single finite number, but it might not. So let's observe now when you start to add these up, and what do we guess? Converges towards a single finite number or diverges? Yeah. So we'll start to add them up. So what would we add up, Denise? 1 plus
1/3.
and what do we? So now notice what we get: 1.33
Mm-hmm.
plus what's the next term?
1/9.
Oops. And we went from 1.333 to 1.444. So the question is, guys, as we keep adding up the next term, 1/27 plus 1/81 plus the next one forever and ever, is this sum just going to keep getting bigger and bigger and past 1.5 and 2 and 3 and 10 and 100 and 1,000 and get bigger and forever? Well, that's diverging in one of these three. Or is it going to get closer and closer to some single finite number? And we don't care if it's 0 or any other. For the second question, we don't care when it converges to which one of these two. We just care what single finite number is it. So right now, maybe it's too early to guess, but if you had to lay all your $1 down that we have, or I have, to my name, what would you guys, if you had to make a bet, what would you bet right now? You think it's going to make it to 2 or to 1.5, or it's going to pass it?
It's going to pass it?
Okay, well, let's find out. What's the next number, Joshua?
1/27.
And what did we get to now? 1.48? We didn't make it to 1.5 yet, but we have a long ways to go. Forever. But what's the next term going to be, Joshua?
1/81.
And we got closer to 1.5, 1.49. We didn't pass it yet. The next term would be, even though I didn't write it over here, but the next term would have been 1/3, again, 81 times 3, 3 times 243 would be the next term right here. Remember, these individual terms are getting smaller and smaller to 0. That was this first question.
Mhm.
So that means when you start adding them up, there's a chance that they will converge, but they might not. We don't know. So we're exploring to find out. So add 1/243. Did we make it to 1.5 yet?
No.
No.
No. Plus, so right now we're like, maybe you're starting to change your mind a little bit and you might be thinking, I don't know if it's even going to make it to 1.5, not to mention 2 or 3 or 10 or 100 million. Yeah.
Mhm.
What would you guys guess now that we have a little more information? You still think it's going to pass 1.5 or maybe pass 1.5 but never make it to 2 or never make it to 3, or you think it's going to just keep getting bigger and bigger still?
I don't know anymore.
You don't know anymore.
I feel like it'll maybe get like to 1.5, but it'll never get to 2, I think.
Okay.
Because
So
I feel like
let's-
if we keep adding fractions, I know it'll be a little bit that you're adding, but you're still adding something.
Yeah, that's now you're thinking the way we want you to think. And that's kind of the beauty of all this. I'm not sure if I can multiply 3 times 243 in my mind anymore.
729.
Oh yeah, I should have known that one. What happened?
It's getting there.
So let's see. Now you might start to change your mind. You might not. I don't know. What's the next one going to be? I have to know what 729 times 3 is.
2187.
Did we get to 1.5 yet?
No.
Now what do you think, Joshua?
I think our limit is 1.5.
What's the next one?
65, 61.
What do you think, Denise?
See, now there's 3 9s.
Yeah. We got closer to 1. We're getting closer to 1.5, aren't we?
Yeah.
But the question is, are we going to make it and pass it or not?
Okay.
You understand?
Yeah.
And that's what we're trying. That's what this second question is. What's the only chance this can converge to a single finite number? When is the only chance that it could ever happen? Which is difficult. It's when the end of the first question, which is what's happening with the individual terms. The only chance for this sum, infinite sum of the terms to get converged towards a single finite number, maybe 1.5, maybe something else, maybe 2, is if what? The individual terms get closer and closer to what?
0?
0. That's the only chance. If it converges these individual terms towards a single finite number, but something else, like a 2 or a 1.3 or a -4 or whatever, well then there's no chance for these terms to converge towards a single finite number. Yeah? So not to mention is if these individual terms don't even converge to begin with, but they diverge, well then this has no chance as well, and you just write diverges right away.
So then for our sum limit, the only time it'll converge is when it's at, the individual limit is at 0, but that doesn't mean it's going to converge to 0 as well, right?
You said almost everything correct, but got a little bit off. So the only chance for the sum of the terms to converge is when the individual terms converge to 0. That
Right.
part was correct. It does not mean that the sum of these terms will converge to 0. Did it look like these terms are converging towards 0 or towards 1.5?
Towards 1.5.
Yeah. Could they converge to 0? Yeah, only if these are alternating terms, like positive, negative, positive, negative. Otherwise, you keep adding a positive number to itself, and you're never going to get closer to 0. Does that
So
make
it's
sense?
just for sure that it's going to converge toward a number.
No. If you get the individual terms converging to 0, like this one, that only means when you start to add them up forever, there's a chance that the sum will converge to a single number. It may not.
And that's when we have to further explore.
That's when you do the further exploration, which we're doing right now. And we're doing it right now, but by observation and not by any mathematical test. Yeah?
Okay.
So in a moment, we're gonna have a homework problem where these individual terms get closer to 0. And you're like, oh, that means there's a chance when you add them up, it could converge, but it might not, and it might diverge. And on some of the problems we'll do, and the individual terms will be getting closer and closer to 0, which means, oh, there's a chance when you add them up forever, there's a chance that it'll converge to a single finite number, but it turns out that it won't, and it'll still diverge. It won't get closer. The sum of all the terms will not get closer to a single finite number. They will either get closer to infinity, to negative infinity, or the sums as you go out alternate. Alternate not towards a single finite number, but alternate to more than one single finite number. So I might have lost you right there at the end, but so Joshua, do you understand that when this first question is 0, that doesn't mean for sure the sum of these terms are going to converge? That it's
That's
just
the
a
only
chance?
possibility.
And that's the only time it's ever going to be possible for this sum to converge. Only when you get the individual terms going to 0. And if you think about that, guys, in a common sense way, hey, the only time you start adding up numbers forever, the only way, because Denise said it a moment ago, hey, we keep adding a positive number, well, the sum's going to get bigger. Yeah?
Mm-hmm.
So you would think if I keep adding a positive number and when I keep adding another positive number, the answer is going to keep getting bigger. And that's correct. And the only way that it ever can get bigger and bigger, but closer and closer to like 1.5 or anything else, is if these terms individually are getting closer and closer to 0. That's the only chance.
Okay.
Because what would happen, so we're super close for you two understanding this, what would happen if we had this? I'll just make something up. 1.88, I'm just making it up. 1.89, 1.89, that's a 1, 9, 2, and 1.893. And these terms do converge individually. They converge to a single finite number, and they converge towards 2. Are you with me?
Mm-hmm.
Yes.
That's this first question, which is where here? They converge, the individual terms converge to a single finite number, but which one of these subsets? Did we say it's converging to 0 or to some other number besides 0?
Some other number.
Yeah, what other number?
2.
2. So now what does that tell us then about the second topic of interest? When we start to add these terms up forever,
They will not diverge.
it will what?
Won't diverge.
It will diverge, yeah? Yeah. Because think about it, what starts to happen if you start to add these up? If I were to go on another line on the computer on Desmos, I know I'm kind of writing all over the
Oh,
place.
okay. So because your example lost the chance of ever being of ever converging because the limit was not 0, that means it's never going to be converged, so it's got to be diverged.
The sum can never converge, correct?
Uh-huh. Okay.
I think you just saw the light there, huh?
Yeah. a little.
Okay. So if we start to add 1.88, 1.89, and again, I know we're taking a long time, but if people understand this, then the rest is really, it's so much easier to understand, and the chapter is nice and interesting, and otherwise it's just kind of miserable. What's happening to our sum so far? We added the first term plus the second term plus the third term. You think this is getting closer to 5.7 or 5.8 or 5.999 when we keep adding forever? Or is it going to pass 6?
Gonna pass 6.
Well, of course, because what's the next? Just pretend my made up sequence, because now I'm adding 1.893, and well, of course, now it's way past 6 and it's past 7. And what's if I were just pretend to keep going, whatever, it doesn't have to be just like that, but isn't now it passed 7, it passed 8, and it passed 9. So does this have any chance when you add them up to converge to a single finite number?
No.
No. Why? Because these individual terms were not getting closer, and even though they were getting closer and closer to a single finite number, but it wasn't what special subset, what special finite number.
0.
Does that make sense?
Yes.
Denise?
Yes.
Okay, awesome. Oh, so by the way, this one up here, if you guys had to bet your $1 now, what would you think? Is this sum forever, adding these terms up, gonna keep getting bigger and bigger and diverge? Or is it gonna converge to some single finite number? What do you think?
Converge.
Converge. Towards what?
1.5.
Yeah. But, oops, I lost it. Oh, I can get it back. What is the next term? Just one more. Did you guys do that on your calculator?
19,683.
Whoa, what is it? 19,000? Huh?
683.
683. Oh, you were wrong, Denise. We made it past 1.5. Or no?
No.
No, I'm just kidding, right? Okay, she's like, don't do that. Okay, it's 1.499. There's more nines, huh?
How is that possible? That's like sorcery. That's like
It
playing with my
seems like-
head.
Yeah. Okay, good question. One last, it's a story. It's not a long discussion. It's just a story, but it's a good one. It's a good one to use to answer your sorcery question. Okay, and that is pretend this is a wall in a room, So this is a wall. And that's supposed to be a W. So that's a wall. And the floor is here. So this is the floor. And let's say there's a little microscopic creature. And the microscopic creature is, let's say this is 1 foot away from the wall. And, excuse me. And there's different examples we could use right here, but I'm just making one up. And the microscopic creature is right here. So how far away is the microscopic creature away from the wall, according to my wonderful picture here?
2 feet.
2 feet. Yeah?
Mm-hmm.
Okay. So this creature, well, this may not be realistic, but pretend this creature, the first step, these are steps or hops or jumps, whatever, steps. And the first step is A sub 1. And the first step, this microscopic creature, boy, this microscopic creature can really jump. And it went 1 foot. And then the next step, the microscopic creature goes is half of that. Half of that first jump. Because the microscopic creature is getting tired. That took a lot of energy right there. Okay? So then the second step, well, unfortunately, the microscopic creature is exhausted. It's getting exhausted already. And now it only can jump half as much. So now the microscopic creature is right there. How far did the microscopic creature jump on the second hop?
Half a foot.
A half a foot. And how about, and that took well, he didn't have much energy left after those, and now he or she has even less. So A sub 3 is the next hop, and it can only go half of that. So this is 1 foot, I should have wrote 1, this is a half. And now the next one is half of that. What's that gonna be?
A fourth.
A fourth. So this is 1/4 feet. And this keeps happening forever. Well, this poor microscopic creature sees a big, big, delicious speck of food at the wall and really wants to make it there. But the poor microscopic creature is getting tired, more and more tired as he continues or she continues. So what would be the next step is only half of that. So what's that going to be?
6.
What's 1/2 of 1/4? So you multiply 1/4 times 1/2 and whatever that is.
Oh,
So
yeah.
1 over what?
8.
4 times 2 is what?
8.
8. 1/8 of a foot. What happens if we keep going like this forever? This poor microscopic creature, yeah? The next jump would be 1/16 of a foot. The next one would be 1 over 32 feet, which is not very much. and so forth. 1 over 64. What's happening to this creature's individual steps? As the creature gets more and more exhausted, what's happening to the microscopic creature's individual steps? What's
They're
happening to
getting shorter or they're getting smaller?
Yep, which means the limit as the number of steps goes forever of this sequence, and how about I use M for microscopic creature? What is this limit of every one of these terms of the sequence, which represents the distance the microscopic creature is able to jump each next term? These terms right here are getting what? Are they, oh, I'm asking a limiting question. Are they diverging? Is it converging? Which one?
Converging.
Converging? Which kind of converging? Which kind of single finite number? A 0 or some other number not equal to 0? Which one?
To 0.
To 0. Is that part okay, Denise?
Yeah.
Oh, so what does that mean then? Yeah, that means if we ask the second question, which is, what happens when you do what to these terms? What's the second limiting question that we're going to be curious about?
Does the summation have a limit?
The summation of all these terms, which for the microscopic creature is the total distance this microscopic creature will move, jump, step forever, and you add them up. Yeah?
Mm-hmm.
Well, so now because we got 0, what's that supposed to tell us then about the sum of these individual terms?
That
Yeah.
it might converge?
It might converge. Very good. We don't know yet. Right? We need to do further exploration, right? Correct?
Yeah. Yeah.
So the second question of interest would be, what about the infinite sum of this sequence? The term, oh, I don't know what that is. Well, this either converges or diverges. We don't know yet. Converges. Diverges. Not sure. We don't know yet. We know there's a chance. And that's what's important. Because if there's a chance, then that's when we, of course, if we already know it converges, well, then we're done. But there is a chance that it converges, but it's just a chance.
Okay.
We don't know yet. So there is a chance. So every single problem we're going to do in the next 5 sections, the only time when they ask us about the sum of the individual terms of the sequence added together forever and ever, the only time it's going to be of really much interest is when the individual terms converge towards what?
0.
0.
0.
Because that's the only chance. Then when that happens, then the sum of these terms forever has at least a chance to converge to a single finite number. Because, and otherwise, if you get anything else other than 0, which is this other number not equal to 0, or you get the individual terms diverge to one of these 3 situations, well then, so this is the only one on the initial exploration about the individual terms where we say, oh, now because we get 0, then the sum of these infinitely many terms at least has a chance to converge. And now we need to do some more work. Okay?
Mm-hmm.
Now, what about this one in particular? This microscopic creature problem. So then this is where it gets to, you were saying, what was the word you said? I forgot. Sorcery. Yeah.
Mm-hmm.
Which is interesting. And that's good. That means you're thinking about this a little more deeply than just, yeah. So you're like, if I keep adding something, a positive number to some other numbers, well, isn't it just going to get bigger and bigger forever? Well, that's your sorcery question. And almost all cases you are correct, and there's no sorcery whatsoever, because if these individual terms are not getting closer and closer to 0, then when you add them up, they're always going to keep getting bigger and bigger forever. The only time there's this mystery, which you said sorcery, is when when you start adding these individual terms that are getting smaller and smaller, closer to 0, then it is possible this infinite sum can converge towards something.
Mm-hmm.
And that's the sorcery part. And this is an example of that. Because what's going to happen, Denise, when this poor microscopic creature, if you keep going half and half and half and half and half, unfortunately, this poor microscopic creature is never going to make it to the wall.
Right.
But what's the limiting value if the microscopic creature could jump, let's say it could live for an eternity that was immortal, and it just kept jumping half of the distance, half as much, half as much, half as much forever. Then as you go out for eternity, forever, what would the distance that microscopic creature has traveled get closer and closer to?
0.
How much distance has this microscopic creature going to cover as he keeps jumping forever and ever and ever like this? The 1 foot plus another 1/2, you're already past one, you're already at 1.5 on the first 2 jumps. And then 1/4, and then 1/8 plus 1/16. And what do you think is going to happen if you keep adding this up? Isn't this creature getting closer and closer to the wall?
Yeah.
And how much distance is it from this first position all the way to the wall?
2 feet.
2 feet. Therefore, what is the limit? What is this limit going to be right here as this microscopic creature starts to make these steps, which are these individual distances? Yeah. The limiting value, which is the second question, has a chance to converge or not, but it actually does converge, and it converges to what? What will the microscopic creature's total distance start to approach as the creature continues stepping forever and ever in this pattern? It's going to get closer and closer to the wall, which is closer and closer to what single finite number? Not what his individual jumps are, but the total distance the microscopic creature has traveled, which is the sum of all these. It gets closer and closer to what?
0.
The distance to the wall is getting closer and closer to 0, but how far is the bug traveling? What's that
2
total?
feet.
2. There you go. 2. Is that okay?
Yeah.
So what happens when we add 1 plus 1/2 plus 1/4 plus 1/8 forever and ever? It never will make it to 2.
Mm-hmm.
But it gets closer and closer to 2.
Okay.
because unfortunately the microscopic creature never gets to make it to the wall, even if the creature continues to move in these steps, but it does get closer and closer to the wall, which is what we mean when we say converges towards 2.
Okay.
So does that make sense?
Yeah.
Does that take away a little bit of the sorcery part out?
Yeah.
Okay. And that's a normal reaction. A person may not use the word sorcery, but they may use the word, this is unworldly, or goes against our intuition, or something of that nature. So look what's happening here. 1/2 plus 1 plus 1/2 plus 1/4. The next one was 1/8. We're already at 1.875, and that's just after this, and that's the ones I drew. This little brown one was 1/8. And we're already at 1.875. Total is the sum of the first 4 terms, or the first 4 steps, continuing like this forever. But these individual steps are getting smaller and smaller to 0, which means, again, that the sum of these terms at least has a chance to converge, and they are. What are we getting closer and closer to?
2.
To 2. And go like this forever. And we're already at 1.99, and we could keep going, and you will see that it does keep getting closer to 2, but it'll never make it, because you can never, this goes on forever. So we can say, yeah, we know we're getting, now the computer is going to give up and say 2, just because of the limiting computation capacity they program this to be. But I hope that makes sense. Okay?
Yes.
Okay, so you've learned almost the entire, well, you've learned the idea for the rest of the chapter. It's just what you haven't learned are the individual, what's going to happen on every single problem we have. We're all going to do the first step, which is to look at the limit of the individual terms of the sequence. And what's going to happen if we don't get 0? If we do not get 0, if we get anything else, which is some other finite single number, which means the terms, the individual terms converge, but not to 0. That's this one. Or if it diverges the individual terms, which means infinity, negative infinity, or an alternating, then as long as we don't get 0, then the second question, which is the limiting value of the sum of these terms forever, we're going to know right away it's going to what?
Diverge.
Diverge. And that's the first test that this chapter writes in the book, because the whole idea is based on all of this lengthy discussion that we've been going through. So that's why when we start to learn all these tests, the first thing we always want to do is look at the individual terms of the sequence. And if we don't get 0, well, then we're like, okay, well, then the second question, there's no doubt that the second question, the sum of all these terms are going to diverge. We're done. And the problem takes 30 seconds or whatever. When will it be more interesting of a question? And so that we can learn all the proper tests for this chapter, we're going to get a lot of made up questions where the individual terms are going to converge towards what?
0.
0, because then we have something interesting in terms of what about the individual, the sum of all these terms. We know then it could either converge or not. And then we need to use whichever test is appropriate.
Okay.
do we kind of see the big picture? This is all that big picture I'm trying to talk about, but it's so much
Yeah.
for 20 minutes. That was ridiculous for me to think that. I'm always eternally optimistic that it won't take long, but it always does. But I hope that makes sense.
Yes.
So I hope we have the large and most importantly is this perspective about sequences that I'm telling you. So now we move finally to some problems. And we're only going to do the 9.2. I thought we might also learn a couple more. That actually doesn't take very long, because once you learn all this, then the tests, they're very specific and they don't take very long, but it's already been a long time. So we'll just cover 9.2 today. And if I can say goodbye to all this scribble here, it's all gone. Okay, we never did it, didn't exist. It was all sorcery, okay? So now let's go to WebAssign. Oh, I guess I'm already here. And go to this. Okay, you're like, what the heck does this have to do with any microscopic creature, huh? So, am I in the right section? Yeah, okay. So now I need to go to a new page. And now we look at a problem. So at first it's going to look kind of strange and intimidating, but just wait. Okay, so let me just collect my thoughts here to decide how do I want to go about this. Okay. Okay, so let's look at number 2. Number 2. So I know we're probably tired already, but it's going to feel better in about 15 minutes. And you're going to be like, oh, okay. So I'm just going to switch to my notebook here. And here we go. So so this is the sequence, this formula. And by the way, can we always put in front of it here if we want to?
1.
A multiplied 1. Does this look familiar at all, this kind of pattern, this kind of format from your notes before?
Mm-hmm.
It looks like A times what?
R.
To the nth power?
Mm-hmm.
Yeah, very good. And what happens when it's n versus n minus 1? That means they're starting with what are they calling the beginning term?
A sub 0.
Mm-hmm. And here they are, n equals 0. Yeah. And so this is the beginning term, n equals 0 or a sub 0. This is when n equals 1, a sub 1, and so forth. So the first couple of times, it's important to continue with what we were learning, and by getting a feeling for the terms of the sequence. Well, let's do that. So what happens when we put 0 into this formula, which is the beginning term? So what's negative 1/7 to the 0 power? That's just what?
1.
1 times the invisible 1 is 1. The next term is when n is 1. So negative 1/7 to the first power. What's that?
Negative
Any-
1 over
Good. Negative 1/7. Yeah. So this is positive, and then it went to negative. What about the next one? N equals 2. So what happens when you put a 2 there? Negative 1/7 squared means negative 1/7 times negative 1/7, which is what? Negative or positive?
Positive.
And so this one is alternating, isn't it?
Mm-hmm.
And let's put the 3 in. Negative 1/7 cubed would be negative, and it would be 1 over 7 times 7 times 7. What's that? 49. I don't know. 343?
Mm-hmm.
343. And one more. Fourth power,
2401.
what is it?
401.
I didn't hear you correctly, I don't think. 7? Huh?
2401.
Oh, okay. I only heard 401. Okay. And so forth. Okay. Now I know this one's alternating, and that's the first one. I was like, oops, maybe I shouldn't have picked one that was alternating, but it's okay. We can handle it. So what's the first? By the way, what are they asking us right here? What does this mean? Yeah.
The sum of all terms forever.
Very good. Did they ask us to analyze the individual terms? Did they say that anywhere in the question?
No.
Oh, I mean, you might have forgot the question, but no. But we know, we're supposed to now know from our lengthy discussion that we have to first analyze the limiting value of the individual terms before we can move forward, okay?
Okay.
So first step, if you will, is to determine the limiting value of the individual terms, not the sum of the individual, not the sum of the terms. This is the first thing. As they go out forever. So the limit, we can do it by observation, looking at these terms, or we can do it computationally. And this is either going to diverge or it's going to converge because it's a limiting question. Mhm. What's the only determining value we could write right here that will make this question they're really asking us for interesting or somewhat of a challenge? I'm sorry?
0.
Yeah, if we get 0 here, then that's that special case where then we don't know then what will happen if we add these up forever. We don't know if the limiting value of the sum of all these terms will converge towards some single finite number or not. Then we'll have to use a test, okay? So Well, what about this limit right here of the individual terms? We could answer it by intuition or observation or by computation. Observation may or may not make us feel very like, ugh, I'm a little shaky about my observation versus a computation. But, so what are we going to do most of the time? Just compute. By observation, we may or may not be able to have a feeling for it. But yeah, they're alternating, all right. These are the individual terms. This is at 0, and we get 1. And this is at 1, n equals 1, and n equals 2, and so forth. And we go from 1, alternate to -1/7, which is already, it's negative underneath, but it's a pretty small number. The next one is n equals 2, which is positive, which means above, but it's even smaller yet. And the next one is n equals 3, which is a negative number, which is underneath, but it's even really getting really close to the x-axis, and so forth. And the next one is even closer. So, by observation, the limit of these individual, what's happening to these individual terms as they go out forever, what kind of determining value does it appear to be? Is it, which of these 4 determining values for any kind of limit is it? Is it a diverging type where it's infinity only, which means the points would have been going up, 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 up forever? Negative infinity, down, 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 down forever, oscillating or alternating behavior that is not getting closer to any single finite number. Not. It is alternating, but isn't it alternating towards a single finite number?
Yes.
So that means it went from here alternating, oops, and it jumped right back up to here. Because it's an alternating behavior, but it is getting closer to a single finite number. And what single finite number is it getting closer to?
0.
0. Is that okay?
Yeah.
Which is, I'm getting my classes mixed up. Which is this one, and from this one, which subset is it? It's this one, which is the one that we've been talking about. And I hope your mind's already clearly thinking through all this now. And if you are, then you're way ahead of most people that learn this topic or try to learn this topic. So we get 0, which means what? About the sum of the individual terms as you go, I mean, the sum of the terms as you go out forever. What do we know about, what do we know right at this moment then?
That it can converge.
Very good. That it can. It may or may not, huh? Is that okay?
Yes.
Denise?
Yeah, are we gonna compute it?
Yeah.
Okay.
I know Denise does not like that observational style. No?
No.
Okay, I don't blame you. So, by observation, these individual terms, either by looking at its graph or just by imagining it in your mind, they are getting closer to 0. By observation, it converges towards 0. But like Denise is saying, we're gonna really, from now on, we're gonna do it by computation. But it is important that we understand the observation part. But anyway, so by computation, we simply take the limit here. And what happens as n approaches infinity, and you put infinity right here, this may not be very helpful because this just means negative 1/7 times negative 1/7 times negative 1/7. And when you do that, you're really kind of going back up to here, and that may not be very helpful. So then we have to remember this little step right here, which was we could rewrite this as -1 to the nth power over 7 to the nth power. Well, a while ago today, we had something like this, 1/3 to the n minus 1. And then that was a little confusing in terms of finding the limit computationally. And then I said to you guys that if it helps, we could separate this as 1 but the numerator is always going to be 1. It's not even alternating like this one. 1 times 1 times 1, it's just going to keep alternating. So then you just can not needed to write the n minus 1, and we just had this part. And then when you took the limit, 1 over a larger and larger number did converge to 0. And that's what we did on this example a long time ago today. And now the same thing can be done with this one, except the numerator is not just a 1, but it's a -1. And that does add a little complexity to this. So we cannot just say that this is always 1 because it alternates, positive, negative, positive. So we have to leave this -1 here to the n power and write it like this. And I separate it like this for our computation that we're about to do to make it a little bit easier to see. So all this part does is make it alternate. Positive, positive in the numerator, +1, and then -1, and then +1 forever. So, but what about the denominator? 7 to the infinity, what is that? That just keeps getting what? This denominator just keeps getting what? As you go, as n gets bigger, these terms go out. The denominator is doing what?
Increasing.
Increasing. It's getting bigger and bigger. So this is 1 over infinity. 1 over, oh, sorry. So this seems a little bizarre, but this part is just the alternating from +1 to -1 to +1 to -1 forever, which is the same thing we have right up here. 1 over 1, -1 over 7, 1 over, like that. So although it's a little bit bizarre, a little bit out of the ordinary, but really you don't have to really think much about this piece, because that's just what I just said here, the positive, the negative, like that. But this is the part that's important, because no matter if this is at a -1 or a +1 and it keeps going back and forth, but what's this part going to do? 1 over a larger and larger number gets closer and closer to what?
0.
0. And so no matter what +1 or -1 or +1 is in the numerator, which is this part, when you multiply it by times something that's getting closer and closer to 0, this overall will still get closer and closer to what? What's 0 going to be times this either -1 on top or +1 on top? It's still going to get closer to it's still going to become closer and closer to what?
0.
0. So yes, I just happened to pick a problem, and maybe it's good that, or maybe not, that was an alternating one, but still, we still look at the first question is what's going on with the individual terms as we go out forever. And either by observation, we notice they're getting closer and closer to zero, or by computation with this little quirky part, but we still then realize it's getting closer and closer to zero as well. So this, by computation, converges, the individual terms converges towards zero. Any questions there?
No.
No.
So what does that mean then about the initial question? Therefore, what do we know? What can we say right now about this infinite sum? I mean, when you start to add this up forever and ever, do we know right now? Can we say that it's going to diverge for sure or converge for sure, or we don't know yet?
We don't know yet.
Right. There's a possibility. This is the rare chance when this has a possibility of converging towards some finite, single finite number, huh?
Mm-hmm.
Is that okay?
Yes.
Okay. So, how about this? Is still, or it is, this is still possible, or it is still possible for this to converge. We need further exploration or testing. And this is where it's going to start off from now on. We're going to get this first step done about the individual terms. If we get zero, then this will always be the next step statement. It's still possible for the sum of all these terms to converge, and we need further exploration by using a test. I'm going to leave a little space right here because I'm going to fill in a word. I just don't want to do it yet to throw you off. Okay, we need a test. So what would have happened if we do this first step and look at the individual terms and we do not get converges to zero? We get converges to some other number, like a 2, like in the last problem with a microscopic creature, or it even diverges. Then what do we know about this question automatically then? If we don't get zero here, then what do we know about this question right here? It will always what?
Diverge.
Diverge, and then we're done.
Mm-hmm.
Does that make sense?
Yes.
Okay, so this one though, we're not done. So we need a further exploration by using a test. So what test is there? Well, there's a bunch of them, but one of them, so here are tests. And we're gonna have a list. There's a list, I don't remember, I could count, I guess, if I had to. There's 4, 6, 7, 9 of them, I think. There's 9 tests. You could say 10. This initial part, if you don't get 0 and you're done, that's also called a test. So that would make it 10. So we can say 9 or 10, but the way I'm trying to present it to you is there's 9. The 9 tests when further exploration. 9 tests when further exploration is needed. The other test is when we don't have to explore further and we're already done. So that's the nice case, when further exploration is needed. So there's a list, 9 of them. We're only going to look at one of them here today. And that's when it's geometric. When we have a geometric sequence. So on all the problems today, only 2 things can happen. One, when we look at the limiting value of the individual terms of the sequence, we get 0, which means further exploration is needed. And the only further exploration that we have is just this one, the geometric test. And I'm leaving a blank word out here. I keep doing that, but I'll get there. It's not a big deal. And here is that test. The infinite sum, and this could be 0 or 1. I'm just going to put the zeros. That's more popular for geometric sequences. This is an infinity up here of and this is nth power. It could also be this other one. And that's when we start at 1. Will, and this is a very nice test. It's very, very little exploration is needed at all. Will converge, will converge, will diverge if the common ratio R if it has some value, it's going to converge. If it has another type of numerical value, it diverges. But we're talking about the common ratio here, what R is. So remember our previous 2 that I made up? What was this first one? When we multiplied by what each time?
By 3.
Yeah, that's when the common ratio was 3. What's the absolute value of 3?
3.
3. And what happened with this one? We said what? What happens to these individual terms as you go out forever? Do they get closer and closer to 0 or no?
Yes.
No.
No. So what about this individual limit of the individual terms? They're not even converging to some other finite number other than 0. They were what? Converging, or is this diverging?
Diverging
To what?
to infinity.
Infinity. So then automatically we're done. Well, we would be done because this has no chance, these terms, to add up to 0. To add up to any convergent finite number is not possible. What about this one? This is when R was equal to what? What was our common ratio on this one?
1/3.
1/3. What's the absolute value of 1/3?
1/3.
1/3. And this one, the individual terms do get closer and closer to 0. So that means there's a chance that it converges, the sum converges, and we would do further exploration. What's the further exploration, the test? Well, it's because these are both geometric. You would use the geometric test. And what do you do with the geometric test when you have a geometric sequence? You get your common ratio, take the absolute value of it, and then you compare it to the following. If the absolute value of the common ratio is less than 1, it converges. The sum of those terms forever will converge towards a single finite number. And if the absolute value of your common ratio is greater or equal to 1, then the sum of all those terms forever will diverge. And there's one extra bonus on the geometric test. Bonus piece of information. On most tests, when the sum of all the terms converge towards something, that's all we'll be able to do is say they converge towards some single finite number. Like the microscopic creature, we were able to figure out by observation that the sum of all his steps was getting closer and closer to the wall, which was closer and closer to 2 feet. That's when we know the summation of all the terms forever converges towards a certain specific finite number. Most of the time we won't be able to tell that. But when it's geometric, we will. And the bonus piece of information is we will actually know what the sum converges towards. So not only will we be able to say the infinite sum converges towards a single finite number, but we'll actually be able to find out what it is. And that sum of the terms of the sequence from whatever 0 to infinity converges. We already know it converges because we have the absolute value of r less than 1, but it converges towards what sum? Towards a times 1 over 1 minus r. Every single time. So I could show you the microscopic bug one, but it's already getting incredibly long. So, okay. So then where are we at on our problem number 2? It is geometric. The first step, we took the limit of the individual terms and it converged towards 0, either by observation or by computation, which means it's still possible for the sum of all those terms, it's still possible for it to converge. So we need further exploration by using a test. What test is the only one we have is the geometric sequence test. And what is that sequence geometric test? It's if you figure out what the common ratio is, r, take the absolute value of it, and if it's less than 1, then the sum of all those terms converges to what finite numerical value for the sum? A times 1 over 1 minus r. If the absolute value of your common ratio is greater or equal to 1, then you say the sum of all those terms do not get closer and closer to any single finite number, and then you say it diverges, and then you're done. So, what was our common ratio? What was the common ratio for problem number 2? R was equal, I don't know if we even wrote it down. Oh, we knew it right here because it gave it away, but only if we understood. Otherwise, we would have to take 1/49 divided by the previous term and take this one and divide it by the previous and see if we get the same number. And we would. And it would be what? What did we already say it is? R is equal to what?
Negative
Negative 1/7.
Okay, so it's like if we're running a marathon, 26.2 miles, we're like at the 24th mile right now, and this is when people start to lose it in their minds. Yeah, but anyway, so hang in there. So the common ratio is negative 1/7. So using the geometric, okay, I'm finally going to give you the darn word. The word I have blank here all the way around here is, there's another sophisticated word for the idea of when you add up terms of a sequence forever. And when you add them up forever, and that's what you're interested in exploring, that's called a series. A series. So don't worry about the word. It's just that simple idea of taking a sequence and exploring what would happen if you add them up forever. Does it converge towards a single finite number or not, which would be diverges. Okay? So that's that new word, series. So the 9 test is a geometric, the first one is a geometric series test. But we are looking at the sequence, because the sequence is what are all the individual terms. And now we are just interested in not only what happens to the individual terms as you go out forever, which is our first step, but then what happens when you add them up and you keep adding up one more term, one more term, one more term. That's that second curiosity determining value, limiting value question. That second one is the series, is when you're looking at the series, which is a really strange way of saying what happens when you add these up forever and ever. What are they doing? Converging towards a single finite number or not? And not means diverging. So please, let's try not. That's why I purposely wait on this word series, okay? Anyway, so using the geometric, because then students kind of, okay, series, sequence, what's the difference? And it really throws people off. So don't even worry about the word series. All that just means is take the geometric sequence, and we're curious about when you add the terms up forever, what does it do? Does it converge or diverge? And as soon as you ask that question about adding up all the terms of the sequence, well, now you're saying, now you're talking about series. So that's it. Okay, using the geometric series test, the absolute value of R, in our case, is the absolute value of 1/7. And what's the absolute value of negative 1/7? It's what? Still, well, the absolute value of a number just means
1/7.
yeah, how far away from the number 0 are we on the number line? So we're 1/7 of a unit. So it's 1/7 of a unit. And now, what is this 1/7? It's either going to be this first situation, which means it converges. The sum of all those terms converges towards something, and then, or it diverges. So what does this say? When it's less than 1?
Mhm.
Yeah. And this is when you're either equal to 1 or greater than 1. So which one is this? This one is which one?
Less than 1.
Less than 1. Good. Therefore, or thus, by the geometric series test, there's that darn word, don't let it mess with your head. Yeah? This infinite sum of does what? What does it do when it's less than 1? It what?
Converges.
Converges. What does converge always mean for any limiting question? Towards a single finite numerical value. And of all the 9 tests that you're going to learn, this is the only one that when you get that the sum converges towards a single finite numerical value, that we're actually going to be able to figure out what single finite numerical value. Yeah, this is the only one. All the other tests, we're just going to stop and say it converges towards a single finite numerical value, but we won't know what single finite unless we explore. And we could always explore by, when I say explore, I don't mean using a test. I mean by going to a calculator and just start to add them up and see what it looks like. That would be the only way. Okay? So what does this converge to? Because it's geometric, we do get the bonus piece of information, which is this. The sum of all those terms forever converges towards what single finite numerical value? This, which is A times 1 minus over 1 minus R, or what was our beginning term of this sequence?
1.
1. Times 1 over 1 minus, not the absolute value of R. Doesn't say absolute value, it says R. What was our R? And don't say 1/7, it was what?
A negative 1/7.
And now we compute. Well, this one we don't need, times 1 over 1 minus a negative is plus 1/7, which equals 1 over 7/7 plus 1/7 is 8/7. 1 over 8/7 is the same thing as move it up and reciprocate, which is 7/8. And I know, I hate to think what your minds are thinking right now about how long it's taking, but there we have it. Now, I've taught you everything in this section except to just practice and polish up a couple phrases. That's all. So we go back to WebAssign, and then the rest of the lessons, the 4 sections after this one, we just say the same discussion, except we just come down to our list and we use a different test. And all you have to do then is learn the different tests. And that doesn't take long. Okay, so that was this one. So, and now you see the word series, which just means it's this sequence, but add up the terms forever and see if it converges towards something or diverges. It does converge. And we got the bonus information because this is geometric. And we got that it converges to what? The sum of all those terms get closer and closer to what?
7/8.
7/8. And check. Okay, and we are correct. Okay, now I know you're probably worn out, but it really is going to make a difference. We'll stop in 10 minutes and then that's it. But those 10 minutes, you're going to feel much better about what all this is about. So let's do, for example, number 8. And we have the summation from 1 to infinity of arctangent of n. And did you see WebAssign right now?
Mm-hmm.
Okay. Now to the notebook. We could write out a bunch of terms, although it really may not help much. A sub 1, A sub 2, and so forth. But when you plug it in, you get arctangent of 1, arctangent of 2, arctangent of 3, and so forth. So we would have to plug this into a calculator to write the decimal numbers down and see what's happening to these individual terms. Are they converging towards a single finite number, and specifically 0? Because then that's the only chance that when you add them up, it can converge. So what do we do first? First step is always, what's our first step always? To try to understand if this limiting sum of all the terms converges towards some number or diverges. We do what first?
Determine the limiting value of the individual terms as they go out forever.
Excellent. Which is, you could do it by observation, but there's this lady I know that likes to do it by computation. I don't know who that is. So, and that's what we should, I mean, you could do it either way, but. Well, what about this now? What's the only thing that's gonna, what's the only answer we can put right here that will make us go further and explore further? If we get what determining value right here? I'm not asking you what it is, I'm asking you, what's the only number we will, if we get a certain number right here, then we won't know yet if the sum of these terms converges or diverges. That's when we get what right now? If we get
0.
what? 0. So what happens if we get some other number? What if we get a different number than 0?
It diverges.
We're done, aren't we? Correct. Like the other problem when we got the individual terms 1.8, 1.88, 1.89, they were getting closer to 2.
Mm-hmm.
And then we could say we're done because we didn't get 0. Therefore, when you add up those terms, there's no way they're going to converge towards a single finite number. They will diverge. So let's see what happens with this. What happens with these individual terms? So we got to remember that picture that we had a week or two ago. So now you'll start to see these things that we did earlier will start to pay off. And remember, arctangent looks something like this. And what happens when you go out forever and ever to the right? The graph goes closer and closer to what?
Pi halves.
Mhm. So this equals pi halves, which means if we put these in our calculator, they would get closer and closer to whatever 1.57 something is pi over 2. And so what happens, class, when these individual terms are getting closer and closer to this is a single finite number, which means this limit converges. The individual terms are converging towards a single finite number. So it does converge, the individual terms. But it's not equal to 0. It's pi halves. Therefore, presto, what do we know about when you add up these terms forever? Is there any chance now that they could converge towards a single finite number, or no chance?
No chance.
No chance. No chance to converge. To a single finite number. What's another way of saying there's no chance that it could converge to a single finite number? What's a shorter way to say all that?
Diverge.
Diverges. And by the way, what happens when we take a limit and we know that it diverges? There's only 3 possibilities when it diverges. What were those 3 possible what are those 3 possible things when any limiting value diverges? What are the 3 possibilities?
Infinity, negative infinity, and oscillating.
In oscillating, yeah. So which of these 3 do you think this diverging limiting value is? When you start to add up these terms forever, yeah, do you think that these, and by the way, these are numbers over here on the graph. It's like this one and this one and this one and this one. They're positive numbers. So when you just add up these positive numbers forever, and which one of the 3 is it? Are they going to add up to negative infinity? Well, they can't, because all these are positive numbers. These are all positive numbers. And alternating or infinity. Alternating would mean when you add this one plus this one, maybe you get a negative answer, but close to 0. And then you add the next one and you get a positive answer close to 0, like that alternating. Or, so which one of these 3 do you think is this diverging when you add up these forever? Infinity only, negative infinity, alternating. What do you think happens when you add this plus this plus this plus this, knowing that these are all positive numbers? Yeah, and they're getting bigger and bigger, by the way, closer and closer to pi halves.
Goes to infinity.
Approaches infinity. Very good. So they may or may not ask us. If they did, that would be nice, because that would determine how well we're really understanding all this. Now, this diverges because no chance to converge to a single finite number, because the limit as n approaches infinity of the sequence was not equal to 0.
Mm-hmm.
We have pi halves, right? That's the reason we know that there's no chance for this sum of all these terms to converge to a single finite number because this happened, which we already had up here. I just read it again. There's a name for that, and that's a simple case that you always we're kind of being like, oh, I want to get done with the work. Then fastest problems are always going to be when you're asked to analyze the limiting value of the sum of infinitely many terms. The quickest possibility is always going to be when you do the first step and you get a single finite number that's not equal to what?
0.
Not equal to 0, which means you get, like we got, a pi halves, or you get infinity, negative infinity, alternating for the first step. Any one of those, then we're done. Yeah? And that has a name when we're done. And so because the limit is n approaches infinity of arctangent is not equal to 0, that was that one case. That was wherever I wrote it. Oh, I just wrote it this way. Single finite number converges into one of the two subsets. And if we don't, this is the only case when you have to, when we still won't know yet if the sum converges or diverges towards, okay? And so if we don't get this on the first step, that means either we get this one, which just happened, we got pi over 2, or we could get one of these three, which is the individual terms diverges. If we get anything other than this one, then the summation is done, it diverges. And there's a name for that. I didn't write the name down because I wanted the idea to be there. That was more important. And that name, we can give it a name now. And that name is, because of this, we know the sum diverges. It has no chance to converge. And if you want to say the name, it's because this happened, then we can say this diverges by the nth term test, nth term series test for divergence. I'm like, what the heck is that? And that just is a fancy way of saying, hey, the sum of all these terms of the sequence diverges because when we did the first step and took the limit of the individual terms, we did not get 0. We did not. So then there's no chance for the sum of all those terms to converge. There's no chance. I taught you the idea versus just saying the name, because then I think you would learn more that way. But now that is the name. Okay? Okay, and now you've learned, that's the polishing up, and now it's just a matter of practice. So, and this one, it seems kind of anticlimactic here. You just write what? Converges or diverges?
Diverges.
Diverges. Seems kind of cheap there. Diverges. Okay, let's do one more problem and we'll stop. And then I'm going to tell you, okay, maybe a couple of these you want to wait until, oh gosh, today's Wednesday already. I guess you can try them, read it, or I can also help next Monday and do a few. I guess I can change the due date then. But I mean, it's getting to be unreasonably long, or maybe we're past that already. But so let's just do one more. And I would say if you want to, um, what do you think this kind of formula is right here, guys?
A times R to the nth.
Mm-hmm. So this is geometric, isn't it?
Mm-hmm.
And what's the R?
9/10.
And what's the absolute value of R?
9/10.
And what does that compare for the geometric series test?
Less than 1.
Less than 1, which means what then? By the
Converge.
geometric series test, when you add up these terms forever, they're going to have to what?
Converge.
Converge. And we didn't even, the geometric test, I don't necessarily like this part, but we even skipped the first part. We skipped step 1. We didn't even check if these terms go closer and closer to what?
0.
0, but they would. But because it's the geometric test, you can skip that first step and not even check and just use the geometric series test and look at the absolute value of R. You're like, why didn't I say that to begin with? Because then it's a shock when I don't teach it that way, and now for all their other problems, we have to check and we have to do the first step. Okay? So what are you going to say for number 11? The absolute value of 9/10 is 9/10, and that's less than 1. So then what do we know about this geometric series, which means when you add up those terms forever, they're going to what?
Converge.
Converge. And because it's geometric, don't we get a bonus piece of information? And we can actually figure out, compute what they add up, what the infinite sum converges towards. What happens when you add the terms up forever? They get closer and closer. We can actually write down what that is. And what was that formula? So we know this converges because it's geometric. The absolute value is 9/10, which is less than 1. So it converges. Now we're going faster, and if we don't, can you hear me now?
Yeah.
Yes.
It's because someone was trying to call me, and who's my boss, by the way, the dean of the college. I don't normally ignore him, okay? You guys are important people, just so you know, okay? Well, you guys make the school go or not, so you're more important. Okay, anyway, so what does it converge to? This. So now we got to know our beginning term. So 1 minus 1 minus R. What's our R though?
9/10.
What's our beginning term? Our beginning term is when n equals what?
0.
0. So beginning term is when n equals 0, and you put a 0 right here. What's 9/10 to the 0 power?
1.
1 times 4?
4.
4. So the first term is 4. So that's the beginning term is 4. So it's 4 times 1 over 1 minus 9/10, which is 4 times 10/10 minus 9/10, which is 4 times 1 over 1/10, which is 4 times 1 over 10 is times 10. And what's 4 times 10?
40.
40. So if we were to add up these terms forever, they do converge. They get closer and closer to a single finite number, which is 40. It'll never make it to 40, but it gets closer and closer to 40. So here we would put 40. And we are correct. So this is what I'm going to do, guys. Because it's so long, it's been 3.5 hours, which is crazy. But really, I feel like this is what's necessary to give people a chance to learn this correctly. Unfortunately, not most people don't get this kind of length of time to learn it, and so because of that, we teach it faster, and most people won't really understand it. They just kind of try to survive, or you take forever and not get very far through the course, and so what do most teachers do? Try to find somewhere in between that, which is difficult. But okay. So what I want to do is, and don't groan or scream, but tomorrow, or let's say no, Friday, I'm gonna make a short video. As soon as I say short, everybody goes like, sure. And I'll make it at 11:30. You don't have to join if you don't want to, but I'll make it and I'll go over some more of these problems, but it won't take long because I've already taught all this stuff. But instead of taking another 20 or 30 minutes, if you want to do it, if you guys want to wait on a problem, I would say wait on 4, 5, 6. And let me just say this, is this one here going to be geometric? Does this look anything like the a times r to the n type or n minus 1? Does this one right here?
No.
No. So if it's not geometric, you have to do that first step, just like this was not geometric. So what's always the first step? And we could do it even with geometric, but what's the first step we always have to do? Take the what?
The limit.
Of the individual terms, right?
Mm-hmm.
And so what's going to be the limit of this one? What happens if you put infinity here and infinity here? You get infinity over ln of infinity is still infinity because of this. So what's going to this is ln. So what happens when you take the limit here to start out? You get infinity over what?
Infinity.
And is that determinate value or indeterminate?
Friendly determinant.
Friendly. So what do we got to do when it's friendly? Use what?
L'Hopital's.
L'Hopital's. And what's the derivative of n?
1.
1. What's the derivative of ln of an inner function?
1 over x.
1 over x, or in this case n, times the derivative of the inner function. What's the derivative of x or the derivative of n with respect to n?
1.
So what's 1 over n? So it's 1 times n over 1 if you bring it up and reciprocate it. And so 1 times n is just what?
N.
N. And now what happens when you take the limit as n approaches infinity of just n? Do we get, remember we're on the first step, the individual terms out forever and ever. And do we get a single finite number? And if it's 0, then we continue on. Do we get converging but a different number than 0 and we're done anyway? Or do we get diverges and we're done still? What's the limit now as n approaches infinity of just n? What happens when you just, huh?
Diverges.
It diverges to infinity, huh?
Mm-hmm.
So what happens when the individual terms do not converge to 0 and you get anything else, which in this case we got diverges to infinity? That just means those terms are getting bigger and bigger and bigger forever. So therefore, what do we know about this second question about the limiting value of all the sum of all these terms? We know that it has to what?
Diverge.
Diverge. Because why? Because the first step when we took the limit, we did not get what? Because we did not get what?
0.
We did not get 0. Because the limit as n approaches infinity of the individual terms, this is supposed to be an n, was not equal to 0. We did not get 0. So that's why we know the sum of all the terms diverges. And it would diverge to infinity if we thought about it. And what's that name at the last moment I told you? By what happens if we never have to go to our list of 9 tests and we only have one, and it's geometric series test? What's the fancy expression of words that is this reasoning right here, right here? What did we call that? Because of what test?
Nth term series.
Nth term series test. Nth term series. They don't write the word series in the textbook. They just write nth term divergence test. Or they say the nth term test for divergence. The nth term, sorry, I lost a word here. Nth term test, but we could call it series test or not. Sorry, for divergence. That's the reason that right here, we will put diverges and then click submit. It seems awful cheap just to put one of those 2 answers there and get credit or not, but, oh, and I think I wrote, oh, I did click it right. I clicked diverges, okay. So, any questions on this one?
No.
So then what I wanted to say to you is, if you want to wait on some problems, then I think the reasonable ones to wait on, if I scan through this, would be number 5, number 6, that's it, as long as I make one more comment, and that is on these last problems, 12 through 15, oh, they tell you on some of them, what do they say this is? What kind of, these terms are coming from what kind of sequence?
Geometric.
Geometric. That means you can use the geometric series test, which means you just need to figure out R, the common ratio.
Mm-hmm.
And once you figure out the common ratio, then you just take the absolute value and then you use the test. Does that make sense? So how could we find the common ratio for this one? So this will take like a minute. How can we get the common ratio R for this problem? So remember, you take any term and divide it by the one before it. So that's, I just messed, this is a plus. What's the term right before this one?
A -1.
Mhm. And if we divide 1/9 by -1, we get -1/9. If we do it a second time to confirm, then we'll see if we get a common ratio or not. And what if we took this term divided by the one before it? We would have -1/81 divided by the one right before it, which is 1/9. Move this up and multiply by the reciprocal, and we get -9/81. Reduce it, -1/9. Isn't that the same ratio we got when we tried another two terms?
Yes.
So then do we have a common ratio?
Yes.
Yes, which is letter R. And what is the common ratio? It's -1/9. And now you can use the geometric series test, which is take the absolute value of this. What's the absolute value of our R?
1/9.
What's that? 1/9. And what are we supposed to compare it to for the geometric series test? If it's what?
If it's greater or less than or equal to 1.
It's greater or equal to 1 or less than 1. And which one is this one? Is this greater or equal to 1 or less than 1?
Less than
And 1.
Less than 1. Therefore, what do we know about this? When you add these terms up forever of the sequence, which is called, don't get hung up by that word, series, just means when we add these up forever, they are going to either diverge or converge. And what are they going to do if the ratio, the absolute value is less than 1? It what?
converges.
Converges. So the series converges. And what happens when it's geometric? If the series converges towards a single finite number, we can actually figure it out with this formula, a times 1/1 minus r. And then that's what they're asking for. They're already even telling us it's converging. But we just proved it here. And now what does it converge towards? Well, what's the beginning term?
9.
9 times 1/1 minus, what was our R? Before we took the absolute value, what was our R?
-1/9.
Mm-hmm. And now we compute. So this is equal to 9 still times 1/1 plus 1/9. I'm going hoarse. I'm losing my voice. 1 plus 1/9 is 10/9. 9/9 plus 1/9 is 10/9. This can be written as 9 times, bring it up and reciprocate it, 10/9. The 9s divide out and we get 10. So what do all these terms added up forever and ever get closer and closer to? They converge towards what single finite number?
10.
10. So good. So we can put 10 here and check. Pardon me.
Question. Our A is going to be whatever first value we get, right?
The beginning term, right? And I don't know what happened. I must have, I don't know. Maybe I'm going too fast. So what happened here? 9 is the first term. this did converge, and it was to 1 over 1 minus r. R is negative 1/9 plus 9/9 plus 1/9 is 10/9. So that's correct. So 9 times this moved up is, oh, I messed up. I didn't reciprocate it. What happens when you move this up? It's not going to be 10/9 anymore. It's going to be what?
9/10.
Yeah, I'm sorry. I was hoping that the 9s were going to cancel, I guess. So now what? Multiply this out, and we get 9 times 9 is 81 over 1 times 10 is 10. And we could probably leave it like this as a fraction, or divide it, and it divides perfectly to 8.1. So either one. Well, so first of all, you were asking me a question, Joshua. And I cut you off, but did I answer what you wanted to ask?
Yeah, definitely.
Okay. And then come back here and type in what it's supposed to be, which is 81 divided by 10. Or we could put 8 point, what does it say here? Fraction, integer, or exact decimal. Do not round. So now click it, and we're good. Any questions there?
No.
Phew. So this is, if you divide this divided by the term before it, you'll get a ratio. Do this one divided by this one. If you get the same ratio, that means it's geometric. Take the absolute value. If it's less than 1, that means it converges. And then what does it converge to? You do this. And if it doesn't converge, then you just type diverges here and you're done. So that's these two. And this one. Divide 0.9 divided by 9, or 0.009 divided by 0.09, and see if you get the same ratio. If you do, that's your common ratio, which means this is geometric, which means you can use this test. And then if it diverges, you put diverges, but they already tell you it converges. So you're just going to end up using this formula and compute. So those are friendly once we get to that point. And then this, by the way, this is also geometric, just a little more numbers in there. And what they're asking you here is, everyone, is to do those partial sums. Remember when I wrote S sub 1, S sub 2, like that?
Yeah. Mm-hmm.
And then we added up. This one was the first term only. This is when you add up the first 2. This is the first 3 and the first 4. And then you start to see, hey, what happens? Does this sum look like it's going to diverge or converge to something? And these dots right here are not the individual terms of the sequence, but they're these things. So this right here, whichever graph is the right one for n equals 0, oh, I'm sorry, you would have had to start out here, that S sub 0, because this started at 0. So then you have S sub 1. Okay, so anyway, you figure out all these, and then you match it with whichever one is the correct one here. So for example, 0, if you put 0 right here, what's anything to the 0 power?
1.
1 times 15 fourths.
15
is
fourths.
15 fourths, which is 3.75 from a calculator. And now you would look, okay, which one of these does it look believable? So this says 1, so this is already wrong. So is this one. This one is believable, 3.75. This one is not. and you keep going, well, this is kind of cheap because just by the first term, the first partial sum, you already know which one it's going to be. But I hope you would realize if you did the next one, and then you, to get S sub 1, you would add this one plus whatever you get when you put a 1 in, and that would be the next partial sum and so forth.
Mm-hmm.
And all they want you to do is see the graph of these terms right here, which are the partial sum terms. And then this is another way of saying, hey, what's happening when I keep adding an extra term? I get a new answer, and then another term, I get another answer. Does it look like these sums are converging towards a single finite number or not? And if it does turn out to be the only one that's possible, unless there's more pictures underneath, no. This is the only one that's even possible because it's the only one that starts at 3.75. That's kind of cheap, but what's happening here? See, this negative means it alternates. So you're going from, when you add up the next term, you end up getting a number down here because the next term is a negative number. So when you add it to the 3.75, you get a smaller number. And then when you add the next term, it turns out to be a positive term, which makes it bigger again, and it's alternating. Alternating normally is a diverging type of determinant value unless it alternates towards a single finite number. And what does this look like it's doing right here? These sums, as you keep adding an extra term, you get a new sum. And what are these? These are alternating, but does it look like they're alternating? Does it look like they're just alternating or alternating towards a single finite number?
Towards a single finite number.
So then what would you say about this sequence right here just by doing this analysis instead of using the geometric series test? It looks like this would what?
Converge.
Diverge or converge? Oh, yeah. What would it do? These
Converge.
converges towards whatever is somewhere in here. I don't even know if they ask you. Oh, estimate. So what does it look like it's getting closer to?
2.
Probably 2. And we could guess. That's what it says, estimate. Oh, so this one and this one. And oh, there's the green check mark for our match. And here's the green check mark for the right converging value. And so we also could have gotten 2 by using the geometric series test, and this is your R, and take the absolute value of it, and it's 7/8, which is less than 1, so it converges, and then use A times 1 over 1 minus R, and that would give you 2 as well. But that's not what they wanted you to do. They just wanted you to figure that out by looking at the graph of the partial sum. Okay?
Mm-hmm.
So you do the same thing on this one. And I said wait on 5 and 6, really. If you want to wait on 4, this is the same idea. It's got to be geometric. You just got to figure out the common ratio again and then use the formula. And this one is write down these right here. The first 5 terms of the partial sums. But instead of starting at S sub 0, they're saying start at S sub what?
1.
Which means this is n equals 1, n equals 2, n equals 3, and so forth. So this one right here is just going to be the first term. So this is 1 over 2 times 3 is 6. So right here you would put 1/6. And on this one you would put 1/6 plus, well, now you got to add this term. Well, this is 2 over 12. 2 over 12, which reduces to 1/6, but now add that up, and that you could put it in your calculator. Then they want you to round it anyway. So you would just put this in your calculator, and that would be 2/6, which reduces to 1/3, which is, or you could have all done all that in your calculator, and you get 0.33 repeating forever. So to 4 decimal places, this will be 0.333 stop. So if we check, this is, this one is 0.3333. This one is whatever 1/6 is. I guess that's like 0.17666 or something. So 1/6.166, go 4 decimal places, and then this 6 will go up to a 7. So 1667. So right here, 0.1667. Check. Of course, we didn't finish it yet. So far, so good. And now you would add this term, and then that would be the sum of the first 3. And this is another way to see if we think when we start to add these up more and more, is this going to converge towards a single finite number, or just keep getting larger and larger, which would mean to infinity, which would be diverging. Does that make sense, guys?
Yes.
Okay, Josh?
Yes.
Okay. So really, you would all, I know you're exhausted, but I would say, I mean, you could really do these too, but they're just kind of, there's one little trick. I would just wait on those 2. So I will do 5 and 6 on Friday on a video at 11:30, and then maybe number 4. And if you guys join, or anyone else does, if they have a question, I can do one of these, but that would probably be about it. And then I wouldn't reteach the section or something. That's this long video already. And then next week, then we will start with 9.3, and then all this discussion we've been doing, it's just going to come down to, we do the first step. If we get anything other than 0, we're done. If we get 0, we have to explore further. And when we explore further, if it's geometric, use the geometric series test. If it's not, then there's some other tests that we're going to learn. And that's how the rest of the sections will play out. Okay? So you deserve some kind of medal for hanging in there this long. And excuse me, I think we're close to our record of 4 hours in a couple minutes. But so I hope this helps you. I hope that this all makes sense and it will pay off for you. Okay.
Okay.
Okay. So thanks, guys. We'll see you either office hour or not, or Friday or not, but hopefully by next Monday for sure. Okay.
Yes.
All right. See you on
Okay,
Friday.
guys.
Hey,
Take care. Okay.
you too. Thank you.
You're welcome. Goodbye.
Bye.
Bye.